What if your final AI project could prove that you are ready to solve real world problems using computer vision, recommendation system, forecasting models, and AI agents? That is exactly what this capstone session is all about. Hello everyone and welcome back to Simplilearn. In this video, we will explore the Microsoft AI Engineer capstone and understand how learners can apply everything they have studied in the program to build practical AI solutions. This topic is important because AI engineering is not just about learning concepts. It's about applying those concepts to real business problems. Whether it's detecting objects for autonomous driving, recommending tourist places, forecasting restaurant sales, or even building multi-agent systems, capstone projects help learners connect theory with hands-on implementation. In this session, we will cover the three major capstone projects options. First, we will look into the autonomous driving project where learners use object detection while YOLO and analyze self-driving accident data. Next, we'll explore the tourist project where learners classify landmark images using transfer learning and build a recommendation system using collaborative filtering. Then we'll be covering the sales forecasting project where learners analyze restaurant sales data, create time-based features, compare the regression models, and forecast the future demand. We'll also discuss key technical concepts such as TensorFlow, Keras, transfer learning, image augmentation, pandas, group by data, merging, recommendation system, regression models, and time series feature engineering. Towards the end, we will also move into agentic AI and understand how frameworks like LangGraph, AutoGen, and CrewAI help build AI agents that can plan, use tools, complete the task, and work together. We'll also look at CrewAI travel itinerary demo where multiple agents collaborate to create a complete travel plan. By the end of this video, you will understand how to approach your AI engineer capstone projects and how modern AI engineering is moving beyond simple models into intelligent tool-using AI systems. Before we move ahead, let me quickly share you something exciting for everyone who wants to start a career in AI. Microsoft's AI engineering program is a beginner-friendly program designed to help you understand the complete AI stack, from Python, data science, machine learning, and deep learning to generative AI, NLP, agentic AI, and Microsoft AI tools. The program includes 140 plus hours of training, hands-on learning with tools like Azure, OpenAI, Copilot, Studio, AutoGen, PyTorch, TensorFlow, LangChain, Hugging Face, and more. Plus 12 plus real-world projects and 3 capstones to help you build practical AI. You also get a joint completion certificate from Microsoft and Simplilearn, access to Microsoft certificates, and preprint support for Microsoft Azure AI and certification exams. If you move beyond just AI tools and actually now able to develop and apply in real scenarios, this program is worth it. The link is given in the description box below and in the pinned comments. Go check it out. Before we move ahead, a quick question for you to answer. Which AI framework is mainly used to build multi-agent travel planning system? Is it CrewAI, Excel, Tableau, or Power? Cut answers below. Let's get started.
Okay, so the very first three projects I went through, these are the options that you have to run. And so this very first one is on autonomous driving. It's centered around this idea. And so there'll be, each project has two parts to it. We'll go through both those. This the theme of the first project centered around autonomous driving. This project one, and again, you should have different materials that have the notes or the publication and the insights that are relevant to the project. So again, my goal is to go through these today with you guys so you have a little bit more background on them, and then also review some relevant examples that I think will help you with these particular projects. But let me describe the autonomous vehicle one. So the first part is centered on object detection, right? So we've worked on object detection before, but it has to deal with, what a typical autonomous vehicle system would have to do, which is obviously detect vehicles on the road, for tracking purposes and driving purposes, obviously. Um, and this part of this data that you're going to be working with is twofold. One, it's going to be a bunch of images that we can run object detection on to detect what kinds of vehicles that we are seeing in the image. So there'll be a part one that does that. And then part two to this project will be analyzing some data um, related to accidents with self-driving cars. So there'll be kind of a data frame style data set, and you'll do some analysis. We'll talk about what that looks like, um, related to that data set. So the first part is doing object detection that can predict the vehicle type. So there'll be different models of vehicles, as well as drawing, producing that box that we typically do for object detection, right? That locates the object within the image. And so one of the things I want to do is go back and look at that example that we worked on with YOLO, and just to refresh us a little bit on that process. But in this project, you'll have some data that mimics kind of the example that we went through back then. You'll have images, and then you'll have those files that have the ground truth kind of box coordinates and box label of what vehicle it is. And so, if we have that data, we should be able to follow mostly the same steps that we used when we went through, building and training the YOLO model and then using it for prediction. So I do want to walk through that example notebook because I think that'll be really, really relevant for this. Pretty much identical to doing this, just with different data, right? So this will be predicting different types of vehicles that are in drawing the box around the vehicles within these images. Um, so that's one part of it. The second part is analyze the autopilot program and some of the accident data that I talked about. So there'll be a bunch of different tasks related to that that we'll go through. So part one has images that look like this. So this is part of your data set for this project is the images.zip folder that has all of these image files in them. So you can see they're just images of different types of cars. Maybe some of them are buses, different types of vehicles. Again, our goal is to be able to train and utilize an object detection model, something like YOLO that we did, to be able to draw those boxes around these guys and predict what kind of vehicle it is. Um, so you'll be given data that kind of resembles exactly that kind of data set we used back in that example. Um, so you have images like that. Uh, so then it's all about going through and building the object detection model. So the first task, really the first part of the project, is building that object detection. Um, I know it says here create a CNN architecture, but in reality, you can follow the steps of using a pre-existing model like YOLO. It wouldn't really make a lot of sense to do it by scratch, and not use an existing model that's out there like YOLO. So that's again why I think it'll be relevant to go back and look at that again. But that would be the advice here is just use an existing one and we'll train it with this data. So we won't create one from scratch. We don't need to do that. We can just use an existing one and train it against this data, which is that whole transfer learning process, right? So taking a model that's already been trained off the shelf and then just updating it with our own data in this example. So again, I'll show us how to do that. I'll go back and review that, and it'll be really, really relevant to this. Essentially, a similar task. Okay. So the goal is to train it and then um, basically run that model after it's been trained on some of the test images to see if we can to see what the detection results look like, which we also did in that example back then, right? So we first trained it, which was the transfer learning process. Then we applied that model to uh, some example images to see what kind of boxes it was drawing, right? And so again, I'll go through that today, so we have some review on that. Um, but yeah, that's the first part of it is just doing object detection with this data. Um, so that's the first part. Then well, let me pause there. Any questions on that first part? Again, I think the deep learning lesson 10 that we did on object detection will be really, really relevant to that. Pretty much doing that. If you choose to do this project, I think it'll be pretty much doing that again, and we'll go through that today just to review it. But I think it'll be fairly close to following that. Okay, good. So let's talk about part two of this first one. So this part two will be dealing with this CSV. So part of, again, you'll have the images and their labels, and then you'll also have this CSV for this part two, which has a bunch of data centered around accident cases. Um, and so there'll be some text description, there'll be some statistics about them, um, and whether or not autopilot was being used, how many occupants there were, if there were any deaths. Um, so a bunch of accident data here, and our goal will be to do a bunch of analysis with this. You can see a little bit about the description of the columns. So that's always helpful to know is kind of what each column represents. And so you have some information here about that. So uh, this is, just some information about those columns. So you can see a bunch of different information here, um, including the model of the car, if insurance has been claimed, total number of verified deaths, those kind of things, number of vehicles that were collided with, if any, um, number of cyclists or pedestrians they've collided with, which would be, again, if there were any recorded. That's something to be aware of with this data is there are, it can be null, which means there was no data for that. So if you're doing this project and working with this data, be careful with the nulls in terms of filling them in. I don't think you're building any model with it necessarily. Um, you're not building any model with it. It's just for analysis purposes, it may be easier to fill in all those blanks with a zero, essentially. Maybe something you want to do. Um, but that's just a suggestion. Yeah, yeah, it is legit. It's from a source. You can see like there are rows that have the case sources, which are information about these accidents. Yes, it's old data. It's from 2022, most of these, right? So you can see in the year. Um, yeah, it's older, but okay. So what you're going to be doing with it is some initial inspection, checking for data types. Again, probably the biggest task here is dealing with the missing values. In which case my recommendation there would be likely to fill in with zero, which would be, missing. There's basically no information about it, so we could put a zero in there, um, which I think would be fine. And then you can also remove any columns. So, there's probably columns in there that aren't going to be that relevant, like the case number, an ID, those kind of things. You can feel free to drop them if you want to, just to make the data set a little bit smaller to work with. Um, but part of the exploration you're going to be doing for this is, uh, you know, figuring out how many events there were by date per year and per day for each state and country. So part of what I would recommend there is building it may be helpful to build some images or sorry, some visualizations for this, such as doing different plots like box plots that can use some of these fields like country and state as like the x-axis and count how many accidents there were, how many deaths there were, and those kind of things. Um, you can also, another thing that may help you with this is doing group by. So we can't forget, like, part of our aggregations that we can do on data frames is grouping by different columns, right? So we can group by the country, we can group by the state, we can group by year, and then do totals, like a count of how many events there were. That's kind of what this first one is. This part A is likely just a simple group by. For these things, and then you can aggregate like a count of how many events there. Basically, every row is an event, right? Some type of event in the data, whether that's like a basic accident or a deadly one. They're all some type of accident event. So that's probably the easiest way to go. But you can also go like a visualization route for that too. Um, yeah, it can be. Yeah, definitely. Can the victim be the driver? Yes. There's a column for that in the data. I believe if there was a death of the driver, so Tesla driver, there's a column for that. Yeah. Okay. Then for part B of this exploration is analyzing the death events in particular. So this would be basically filtering the data frame, right, to every row where there was at least one death. Um, so filtering it to that and then kind of analyzing that data frame that you get. So what is the number of deaths in each accident? Which is kind of like an average, essentially. How many of them had the Tesla driver? So that's a count of how many there are with the driver death. Um, what is the fraction of events in which one or more occupants died? What is the distribution of events in which the vehicle hit a cyclist? So what is that? You can even do a value counts there, which gives you that distribution. And these are all columns, right? So the Tesla driver's death is a column, occupants is a column, and then uh, the driver we said is a column. So they're just doing different value counts on columns. You could also just do a histogram, right? That can also be a visual of that uh, distribution as well. And then this is another kind of filter. How many times did the accident involve the death of an occupant or driver along with a cyclist? So that's kind of a filter for did we have a death in this column or a death in this column? How many rows do we have that match that filter? Um, and then how many times did we have Tesla colliding with other vehicles, which is another column, right? So there's a column specifically for that, which is other vehicle. So this analysis is mostly just looking at value counts and just in histograms for these various columns. So fairly straightforward, I would say, for this to do this analysis there. Then you can group by the model and look at the counts per model. So that again could be a very simple graph, like a plot with Seaborn could help you there. It could also be just doing a group by and then doing the value counts once you group by the model and kind of aggregate the count. So there's lots of different approaches, I think, there. Think about what's the best way to get this, get that relevant data and maybe even build a visualization, which I think would be great. And then what is the histogram or the value counts of the autopilot? So there's a column for autopilot. If it's a one, that means autopilot was being used. So that's going to be kind of a filter down to how many rows had autopilot of one. So it's a very simple question that can be answered from the data frame. Uh, so that shouldn't be too bad. So a lot of these correspond to existing columns. It's um, not too much. It's just interpreting those and kind of using value counts, using a histogram to get the distributions of them. Okay. All right. So let me pause there. So this is the first project, one of three. It deals with object detection and then doing some basic data analysis of this event, the accident event data. Um, any questions surrounding this? I'm gonna do object detection examples, um, or just walk through I mean the walking through the example we already did before. So I'm gonna go back through that. After we go through the other projects. So we'll come back and do that. But any questions on this? Okay. Good, good, good. So let me go to we will come back and do object detection. So that'll be very, very relevant to this. The other parts that are relevant to this are likely in our applied data science course. So kind of what we were looking at yesterday with data wrangling, right? So doing those kind of filters and group bys. That was also in lesson four of that course. Um, lesson four of that course of the applied data science, and also lesson 10 on feature engineering probably have some relevant stuff related to that data analysis. But the deep learning course, lesson 10, is going to be really valuable for object detection for that first part. Though, so yeah, let me clarify that is there's three different projects. Each one has two parts. So we just went through the first project, which has two parts. Part one is the object detection for the vehicles, and then part two is data science, data analysis on the accident data. Both of those parts just are for the first project only. So again, you're just going to choose one of the three to do. So if you choose project one, which is this autopilot themed project, you would be doing both parts. So you'd be doing both of those. You'd be doing the object detection and the data analysis, which is all two parts for the first project. So, but again, you only need to choose one of the three projects. It's just each one has two parts. So that actually brings me to let me go to the second project that you have available. Let me share my screen there. So this one is going to be a tourism related, basically enhancing tourism with AI related project. So if you're interested in that, this would be a good one. So uh, in the background for this second project is there are centuries old historical structures that preserve a country's and community's history. To improve tourism, a government agency decides to use advanced machine learning techniques to monitor the condition of these structures and report if any of them need maintenance. Also, understanding customers and their expectation is critical for effective marketing and promotion. A recommendation engine is an excellent way to supplement existing marketing outreach. So, this project is going to center on two parts, as just as the first one had two parts. Part one is going to be a computer vision image recognition problem. So you're going to be looking at different images of structures and classifying them. Um, and then the second part is going to be building a recommendation system using collaborative filtering to recommend a tourism destination given a location. So sort of like item recommendation, kind of like what we've talked about in the past, where if you're browsing a website and you're on a product, you see recommendations for other products. Um, or like if you're looking at a movie, you see other movies. Um, Same kind of thing. If you're at a location, here's other relevant landmarks or locations that are recommended to visit. So That'll be the two parts, is the recommendation part and the image recognition part. So we'll break those down and talk about each one of those, but those are the two main parts for this one. So part one is building as I said, a computer vision model that can predict the category of a structure. So there'll be images, we'll take a look at them, that have different types of structures like bridges, statues, different landmarks, and you'll be basically categorizing those into the different labels. And that's a problem we've done many times is given an image, here's the label for it. That's one that we should feel comfortable with, but I'll go back and review how to do that effectively with transfer learning, right? So we've um, uh, you know, talked about transfer learning in the past and we've done some examples with it. I'll go back and do that as review for this because I think it'll be really relevant to this part one is doing transfer learning with image recognition. So we'll go back and do that. And then part two, we'll be doing recommendation. I'll go back and go through that too, because it's been a while since we've looked at that. Um, so, so those two things, transfer learning, um, I think is lesson 9 in the deep learning course. That'll be really, really relevant for part one. And then, I think lesson 7 in our machine learning course on recommendation, will be, uh, will be, the lesson 7 will be really relevant for machine learning. Okay. So let me dive into those. So part one, as I said, is image recognition, and I think the best way to approach it will be to do transfer learning for it. So we'll talk about that. But this is one of those examples, kind of like the flowers data set that we had, or that had different folders for different categories. So they had like, remember we had like roses, tulips, dandelions, whatever it was, in those different folders. Here we have different structures which have images in these different folders. So we have these are just different structures, stained glass, domes, column, tower, flying buttress. These are all just different images. There's images within these folders that represent those structures. Um, and our goal is to, build a model that would be predicting um, one of these labels for a structure given an image, right? So we have an image, it should be one of these categories of structures. And so we want to build our model to predict that. Um, and there's also a test set so there's a zip folder that has uh, basically training images and test images of these guys. Again, I'll go back and review and show you the relevant notebook that you should use as a guide for doing this. I think it'll follow very closely to like our transfer and learning examples that we've done, where especially like that example where we had different flowers, remember, that were in these folders, and we can load those into a nice Keras data set that splits them into training and tests and all that. So we have practiced before how to do this, and so I think it'll be pretty straightforward to follow those examples. I'll just remind us of that today and go through those. But um, the first task again is related to those images. What we want to do is do some sample plotting. Now this we have examples of doing too. We haven't focused on doing that too much, but we have some code that I'll review today that can help us basically plot some of these images. And so that's not too hard to do. We can load in those files and then easily generate a plot of them. We've been able to do that before. That's not too hard to do. Um, and then the more interesting part, obviously, is building a model. So this is where you want to use transfer learning, right? So I would not advise uh, building it from scratch, even though you could try to put together different convolutional layers and build out your own network. I would recommend using an existing network off the shelf and doing transfer learning, which is what we've done in the past, right? So we have practiced using one of those models like VGG16 or ResNet, loading that in from Keras, and then remember what we did is we left off the last few layers, the top of it is what it's called. Um, and then we inserted our own layers uh, there and then just retrained it on the data, right? So I would recommend going that route. I don't think it makes sense to build your own from scratch. It's not going to, it's likely not to be as effective as one of those existing architectures, which are known to be pretty good. Um, so again, I'll show us that example. I just saw the messages. Yeah, that's true. We did not, we skipped over that. So we need to make those up, essentially. We skipped over those, so I can message offline after this or at the end and clarify that. But yeah, because we need a Microsoft certified trainer to administer that, which is not me. So we skipped over those in favor of just continuing our generative AI material and review. So we do need to circle back to that. It shows completed because in place of that, we covered that other material. But definitely owe those courses. Okay. Okay. So again, and even in these notes, it has a hint to do transfer learning. So of course, that's what I would recommend doing, and we will practice and review what we did back then to do that, just so we see it one more time. Um, so and even says here, modify the top of this network by adding whatever dense layers you want with the activation, and then using dropout if you want. Um, so it's going to be the same exact situation as that example we did. Pull in a model off the shelf, um, you know, leave off the top of it, insert your own layers, and then train that network against the data that we have here in this project. So, and then we know, like, in order to train it, once we have that architecture like pulled off the shelf and we've ripped out the top and we put in our own layers, it's just a matter of setting up the training, right? So we do the usual things. We set up our loss function, our optimizer, which is going to be Atom, our metric, usually accuracy. We can even set a early stopping callback, which is what this suggests to do. So, and that's something we've done in the past, and we can review that too. Um, and then we can basically do the model.fit, right? So we can uh, train the model by running the model.fit once we have everything set up. So that part is fairly easy. And we've done it a lot. It's just getting everything set up from the transfer learning perspective that is worth reviewing and practicing. We'll do that. So one of the things that it wants you to do too in this project, which is interesting, is training the model twice. One time without augmentation layers in the front, which so remember augmentation is those additional layers we put in the very front to generate variations on our images, like doing the zoom or brightness change or flips or rotations. Um, and so it wants you to do training twice. So basically, an architecture that has that at the very front, and one without it, which is, without it, it's easier. You don't have to add anything additional to the transfer learning. But with it, you want to add in the transformations, and we can review that too. Like, how do you do that? Um, but it's essentially stacking together the various transformations that we want to have, and then just putting that in a sequential, putting that first, putting the transfer learning model after that with our own custom layers, of course, but really having that augmentation up front, um, uh, having that augmentation up front. And so we can do it with and without that. And the purpose of doing it with and without it is to see the difference. Like, what kind of difference does it make to have that additional variation? And the idea is like, it should help us generalize, right? If we're able to train our model on those different variations of the input images, we should do a better job of predicting generally against the test set. So it's supposed to help with overfitting. It's supposed to help as a generalization to use augmentation, but we can see the difference in the stats, right? So we should be able to train it and then go back and retrain it with and without the augmentation to see the difference. Okay. So that is the first part. Again, the resources that are going to help you a lot if you're working on this one are the transfer learning, which I think is lesson nine, or 10, 9 or 10 from, I think it might actually be 10 from deep learning. And we'll review that today. So another one on our list. So we'll do um, object detection, we'll do recommendation systems, and we'll do transfer learning. But any questions on this part of it? Okay. Very good. So let's go to part two. So that's part one, image recognition with those different structures, again, using transfer learning mostly. Let's go to part two, which is going to be building a recommendation system. And so, as you would expect, we have different data sets here that represent the users and the items that we would build the recommendation system off of. So we have users in this user CSV. And then we have basically items in this tourism with ID. And the products here, we have to think of the products a little differently than usual. They're not physical products, right? They're not movies. In the examples that we've done in the past, we've mainly worked with movies or like products, right? Here, the product is the location. So it is like these places. So there's a place ID and a place name, like this monument or this, museum or whatever it is. These are different places we could recommend for tourists to visit. And so they have different item IDs, just like any other product would in a typical data set, right? So we have users, products, and which are tourism locations, and they have ratings that are given to them. Um, and so we want to use all of that information to build a collaborative filtering system to give in one of these locations to then recommend other similar locations that may be worth visiting. That's the goal. Um, And so so these are and then there's one more data set, which is the combination of the users and the items and their ratings. So, which of course is the data we really care about, is the users and these different ratings that they gave to these different places. So we should think about these are our items essentially, right? These are our items. These are our ratings for those items. So it's th this part of the project is going to be very, very similar to the recommendation systems that we built back when we were doing like movies or anime. Remember, we had those anime shows and recommendation. It's going to be very similar. It's just these product IDs are now tourism locations that we're recommending. Okay. So, and we'll review that, right? So that's the point of this session, and really next Monday session is to just have some time to review these things as you guys are uh, you know um, working on these final projects here. Okay. So there's a description of each of these data sets. So we have the user CSV, which we already talked about, just contains information about the user's age and user ID. That may not be very relevant for building a collaborative filtering system, but it's there. Um, this is more metadata about the places. So obviously the place ID is really important. But given the place ID, we can use this data to kind of look up what it's called, what a description of it, the actual like city and country location, latitude, longitude. Um, so this is more information about those products. This is the data that we're really going to zero in on, though, to build a recommendation system, right? Is this tourism rating CSV? That's probably the most important data is the actual ratings that were given to these places from users, which are, users, we have to frame it correctly in this. Users are tourists, right? So they are various tourists, and items are places, right? So just like when we were doing users and movies or shows, here we have tourists and their locations. So, but they have ratings that they've given to these locations. So we can certainly build a recommendation system. Okay. So, couple things to do for this part two is first do some preliminary loading of the data and inspection. So check for any missing values. So you want to load each one of those CSVs as different data frames and check for missing values or duplicates, right? Uh, and then basically remove any, maybe drop any missing values or any duplicates we can drop. Um, it says remove any anomalies. So, it may be worthwhile to see if there's any outliers from the ratings. So that may be worthwhile to do is see if there's any really, far away from the average ratings. And we can consider dropping those rows if they're really significant outliers. Um, so, and you can use your own technique to find outliers. So obviously we reviewed a little bit of that yesterday, Monday, various ways you can find outliers, which would be, doing like the Z-score for the rating, figuring out how far away it is from the average and dropping any that are significantly far away. Um, so just do a little bit of that. Um, So then we can analyze the ages of the users. So we can look at the histogram of the age from the user CSV, and then identify the places where these users are visiting. In order to do this, by the way, you likely want to use that second data set. So you want to use um, you likely want to, in fact, you likely want to merge together potentially this user data set with this tourism data set, um, where you can merge them together with the place ID essentially being like the location. And so that may be something you want to do is merge those together so you can answer some of these questions that relate to the user. You may also be able to just use this third data set, which has users and their places and their place ratings. But the goal is there to just answer that basic question, where are the users visiting the most? So what are kind of the top places that users are actually visiting? Um, they might have given them low ratings, but they were visiting them. So what are those place IDs that have the largest count? So basically, value counts on the place IDs, maybe a way to go there. Okay. So then some more analysis. What are the different categories of spots, which is going to come from that second data set? What kind of tourism? Uh, each location is most famous for. What city would be the best for a nature enthusiast? So these are going to be, probably all information we can get from this data set. Um, And there's various ways to do that. Like for instance, the nature, you may look for that string in this description. So you can see is the word nature in this column. Um, or, that's not hard to do by doing a simple filter. And so feel free to use that description column and look for various substrings in there, um, such as nature. That may be something good to answer that question. Okay. And then even here on this part four is create a combined data set with places and their user ratings, which would be like merging the second and third data sets that have the user ID, place ID. If you think about it, we should be able to merge that together because this third data set has user ID and place ID along with a rating, but we have a data set that has information about every single place ID. So we should be able to merge that second and third data set together to have essentially a combined data set. So that'll be good practice for merging, which we looked at on Monday, right? Um, Doing a merging on a place ID, for example. So, and we can figure from that, we can figure out what cities had the highest ratings because the place IDs will be joined together with the ratings. So once you join that second and third data set, you can answer a lot of questions. Which city had the highest ratings on average? Um, which category of places are you have the highest ratings? Again, those are only things we can really answer once we've merged the second and third data sets. Okay, so basic analysis there. Then is the fun part is a recommendation system, right? So then we can use that third data set to build a collaborative filtering model because we have the place ID, the user ID, and the ratings. So the idea is like given a current place ID, um, can we recommend other similar places to visit? The collaborative filtering we want to do here is going to be similar to the examples we did in our lesson that are, it's not user based because we're not given a user, but it's given a location. So it's actually going to be item based, um, collaborative filtering. So we'll review that today. I'll go back to that lesson and kind of walk us through that example. But because again, it's sort of like when you're browsing a product, if on Amazon or something, and you're on that product, we want to see other relevant products that are similar to it that we would recommend. Same thing here. Given a tourist location, what are other tourist locations that are recommended? And so we want to follow the item-based collaborative filtering approach because it's not like given a user what are recommendations we can make for items given that user. It's given the item in this case, right? Given the location, then we recommend other locations. So we'll do item-based collaborative filtering. So we'll go back and review that today. So that'll be super relevant for this project is that recommendation example. Will follow pretty much identical to that, given the ratings data. Given the ratings data that we have and the place IDs and user IDs. Okay. All right. So just to recap that, this second project has two parts. It has a image recognition transfer learning part with those structures, images, and then it has this recommendation, a little bit of data analysis, but recommendation system part two. So those main two parts, if you're really interested in those topics, this would be a great project to do. And so the relevant resources for you, if you really want to do this one, are going to be the transfer learning lesson in deep learning, which we will go back and take a look at today, and then recommendation systems, particularly item-based collaborative filtering, which we'll go back and look at too. So we'll do those two today. third project here, and then after we do that, we'll start getting into some review, go back through some notebooks and some examples we did, that are going to be, I think, relevant to these projects. So the third one is has to do with sales forecasting. So um, in this situation, we are looking at using a model to forecast sales and demand. Uh, and so this is going to be an interesting kind of regression oriented project that is dealing with a bunch of sales data. So if you're interested in these kind of problems, this might be a good one for you. And so we'll talk about it. So we want to predict the demand for various items across restaurants. So the sales that we're dealing with, or sales data that we're dealing with, are for various items that are being sold in restaurants. Um, and so we have a bunch of data around that, and we want to use that to kind of forecast the sales figures for different time periods, essentially. And of course, this is all related to the various data sets that we'll have around these products and how much they were sold over a period of time. So we'll talk about that. So you're going to be working with a few data sets in this, namely the first one is just some information about the restaurant. So each one has a restaurant ID and a name. So very, very simple, as you can imagine. Just basically an identifier and then some name that goes with it. So these are the various restaurants. Now, this data is probably the most important is the sales CSV. So we have different items that were sold for different prices and how many counts of them and which items they were. So there's every row has a date of the transaction, what item it was, what its price was, and then the which is a unit price per item, and then a total number of those items that were sold. Um, so this is the sales data, and then we have information about those items. So we have a store ID, which corresponds to the restaurants. So we can figure out those and we have an item ID, um, and we it has a name, it has a calories, and it has a price, which is the same price that was in the sales CSV as well. Um, uh, so we have items here. So we have three different data sets going on. And as you can imagine, it's going to be useful to combine this information. So in this project, you'll get some practice merging together these data sets. For instance, like here we have restaurant ID. So of course we can merge that to this and basically have a restaurant name per row. That should be doable by joining those together. And then we should be able to figure out the sales as well by merging in that sales CSV because we have, uh, product IDs or item IDs per sales record. So we should be able to join that to this data as well. So we know the name and the calories and the store for every single item that was sold. We should be able to join this together. So we should be able to join all three, and that's going to be one of the tasks in the task list. So just breaking that down, the restaurants, obviously, as we said, only has those two columns, which are the ID and the name, which is the string name for the restaurant. Um, then we have the items, which has an item ID, a store ID, the name, um, then the unit price that we talked about earlier, the name of it. That's another string, kind of fold string description of what the name of the item is. And then we have the sales, and then we have which has the data we really care about, the date, and then the item ID, the price, and then the item count. Um, And so uh, this is all of this data is what we're going to use to do some analysis and then ultimately building some forecasting models off of to predict the sales. So getting into some of the tasks here, the first one is uh, um, importing the data set into Python. So obviously that's just loading the CSVs, and then doing some info and dot head. So doing the usual just basic checks, and then looking for outliers in any of them. Probably the one that we'll care about the most is the sales CSV, seeing if there's any outliers there. Um, and so again, that's up to you to choose what methodology you want to use for outlier detection. You can use the Z-score method. You could use something more advanced like an isolation forest model from scikit-learn. Um, so, but that's the first thing is kind of look for outliers. Now, this is the big part is merging. So we want to take those three that we have and merge them together. And so what we should have is a full data set that has all of these columns included in it, right? So it should have date, item ID, price, item count, item names, calories, store name. All of that information is being brought together in a single data set. So the way I recommend doing this, by the way, is in two steps. So I recommend merging these in two steps. Um, you first want to merge, for example, you could merge the restaurants data to the items data. That you could do it that way. And that gives you a new data frame. Then you take that resulting data frame and merge it with then merge it on the sales data frame. You want to do that in two steps because remember, when you do the pd.merge, um, you really can only merge two at a time. So you pick your two data frames and you pick the column that you're using as the one to look for the overlap. And so what you likely want to do is pick two of them to merge, and then take that result and merge it with the third one. And so by the end of that, you should have a single data set of everything merged together. So for example, like you can merge together this restaurant with the items. That's a really easy merge because this is the ID of the store. So we should be able to merge those together on this store ID. So that should be not too hard to do, because the restaurant CSV has everything, with that store ID. So by the time we merge these two data sets, what we should have is an extra column that represents the name, right? We should have a restaurant name that's merged in here. So we should have that added to it. And that's just from the merging of the restaurant CSV to this one. Then we take that result data frame and merge it to the sales. So we should be merging it to the sales, and the column we can use there to look for overlap is obviously the item. We could use the item ID because every row in the sales has an item ID that's being sold, right? So we can merge that here. And what that should do is bring in extra columns that are um, the name of the name of the or sorry, the sales like amount, like the item count. It should bring in the price, and it should bring in the date, which is important to have too. So we should be able to merge those three together, and you end up with a final data set. So that'll be, a little bit of work there to bring all those together, but that's the point of that task, merging all of it together. And we should end up with all of those columns. Okay. And so if you want a good resource for doing that, go back to the data science course, that lesson 9 notebook that we walked through on Monday that has those examples of merging, right? Those are really good examples for doing this kind of merge here. So you definitely want to look at that as a good reference. That's in the lesson 9 notebook in the data science course. Okay, then once you have all that data together, we then want to do some exploration of it. So one thing we could do is, so when it says examine the overall sales, I think what a good place to start there is plot this based on the date. So essentially what you need to do is generate a new column that is basically the total sales, which should be easy to do because um, you just need to multiply together the price times the item count because this is going to be a unit price that we're selling it for, and then we have how many of those items we actually sold. So if you multiply these two together, you get a new column that is like the sales for that date and that item, right? And so the point is, once we do that, we could group by the date and total the sales. So we can sum the sales column, grouping by the date, and we want to generate basically a plot that shows the sales per day. Right. I think that's ultimately like the best visualization you can get. But you have to do a little bit of work there to group by this date and sum this sales column, which I recommend generating. So the sales column is easy. You just create it by multiplying these two together. Um, and then you can group by the date and sum this sales column per day, and then look at the sales per day. Another thing you can do is once you have this data frame grouped by day, you can resample it. Remember how we had that resample function? So you can resample it to basically go from daily data to weekly and monthly. So you can look into the resample function, which remember you can do like dot resample, and you can pass in like a W here or a month here, capital M, which will basically aggregate it up to weekly data and monthly, and then you can plot that and see how that changes. So all of these will be valuable to do for that exploration. These are things you'd want to do. We have some examples of this in our data science course. If you go back to that and look through some of those notebooks we did, like in lesson 4 with the data frames, um, we have some examples of doing resampling, which remember just aggregates based on that date column essentially. Okay. So that's that's what these first few you can answer all of these questions by doing different graphs like that. So all of these are really um, answering those questions. Same thing with this, like you can look at different quarters. So you can do resample and pass in Q, which will be a quarterly resample from those daily sales. So again, the key here is generating that daily sales column and then just resampling it at different levels like monthly, quarterly, daily, or weekly. Um, so those will answer kind of all of these here, parts A, B, C, and D can all be answered from that kind of view. Um, Then finally, and on this page, what we want to do is compare the performances of different restaurants. So what we can do is group by restaurant. So group by restaurant ID, and figure out, we can group by restaurant and sum the sales to figure out what the top, and then sort it, right? So we can figure out what the top sales selling restaurants were. And we can even look at that across different time windows. So we can group by if we produce this quarterly resample, or I should say, monthly resample, yearly resample, we could group that by restaurant ID and figure out who had the most yearly sales or who had the most monthly sales. So this part E is going to be grouping by the restaurant ID. So, um, that shouldn't be too bad. Once you've done all this work, grouping by the restaurant should be relatively easy. Okay, let me pause there. Um, any questions on this analysis so far? I know it's been a while since we've done a little bit of this. We talked about it yesterday. Um, I say yesterday, I meant Monday. We talked about a little bit of these data frame manipulations. So we'll be doing some more of that, especially the merging here in this one. Group by, uh, resample. The key though is going to be generating that sales column and then grouping by the date to generate a new data frame that has daily total sales. Okay. Okay, so then we can also, so just a couple more is we can also group by the item. So we can group by the item to figure out, and we can group by item and store. So find out which item was the most popular at each store. That's just a simple like group by two columns, the item ID and the store ID. So that'd be part F. Um, and we can figure out if the store with the highest volume, meaning, so volume is item count essentially, is also making the most money. So do they have the most sales per day? Um, that's an easy calculation to do. Once you have that full sales data frame and you can aggregate like the item counts to and aggregate the sales as well. So you may have to go back and do that for part G is just when you do the sum, you group by the date, you can sum the item count and you can sum the that sales column to figure out what the volume is and the money and you can average that out per day. Uh, so and then you can look at the max. So you can look at the most expensive. So you can group by the restaurant and take the maximum item price. So you can figure out what the most expensive item at every restaurant is. And you can also look at what that item's calorie count is. So this is just breaking down, we have this data. We can group by the restaurant and look at the max price, what is the most expensive item. So that's just an aggregation on the price. Um, and that item will come with a calorie count because every item does. So we can grab that too. Okay. So a bunch of group buys that you're going to be doing. So in this project, in the analysis, you should find yourself doing group buy a few times in here. And then we pivot to part two. So that's part one is just analysis. Part two is building the model for forecasting. So part one, just analysis. Part two is building the model. Um, and you're actually going to be building a few different models to do regression. So you're going to be using a basic linear regression, a random forest regression, and an XGBoost regression. So three different regression models. And it even has some suggestions for different features, like what the quarter is, the month, the day of the week. Now remember, you should be able to generate these features from the date. So this is an excellent practice of changing over the date into a datetime object and then grabbing the day of the week, grabbing the quarter, grabbing the month, grabbing the year, day of the month. Those are all things that come from the datetime object. So you should be able to extract those from the datetime object. And so really recommend mapping that date to a datetime object, which we saw how to do on Monday. That's not too hard to do, right? It's just using that PD to datetime function to do that. Um, and so then you want to split apart your data into training and tests. The big thing with this data that is indexed by date is keeping it in order. So you really want to sort by the date, and use the last 6 months as the test and the previous data to the last 6 months as the training data. Okay, so this will involve sort by the date column so that you have it all in time order, and then use the first section of the data. Basically, everything but the last 6 months is going to be the training data. The last 6 months worth is going to be the testing data. So just sort by that date. Um, Now, you may be wondering, what am I predicting? So the thing that you should be trying to predict are the total sales. So it's that sales column that we generated from the item count times the price is the sales quantity. We want to predict that. So it's the sales amount, and we want to build a regression model to predict that. And remember, we're going to have a total of that per day, essentially, right? Um, and so we want to be able to forecast that uh, at different time intervals. So, um, essentially, what you're going to do is you're going to build a model using all of those features to predict what the sales quantity should be. Um, and you will use RMSE. Now, that's a very natural evaluation for the model, because we're doing a regression, right? MSE, we've talked about that many, many times. That's what we would want to use to, if we're doing a regression problem. So that makes sense. And then so you'll compare the performance of those three. So the linear regression, random forest, XGBoost. You'll train all three, take the one with the lowest MSE, that's going to be the best model, and then use that to make a prediction for the next year. So you'll use that to make a forecast for the next year, which would mean essentially making a prediction at the year level. Um, so what would be the next year's sales quantity? Okay. Any questions on this? So something I realized that may be worth reviewing here, and we can do that today, is going back and looking at the resampling. We can do that because I think that'll be helpful for this. We had examples of how to do that, I think, early on in our work with data frames. We can certainly go back and look at the resampling examples because I think that'll come in handy. And also, maybe group by operations too, because this one's going to involve a lot of group by operations, which I think are really handy. We've looked at them before, but it's obviously been a while since we've had to do those. So maybe we can go back and look at those too for review. Okay. So this one, just to recap, has two parts, just exploring the sales data, which is a lot of, uh, like I said, group by different manipulations, maybe even building some graphs, and then building a model off of that sales data to predict the sales quantity. Um, and so if as I said, this might be a good project if you enjoy building those kind of models. So this one, the good thing about this project is it doesn't involve any deep learning, but it is using a lot of older content from, doing regression and doing a lot of group by and resampling and such. Um, so so you have an option to do any one of these three, right? Um, so really good options, I think. All right, so let me stop sharing that. So those are the three that we have. Now, what I want to do is spend some time starting now, reviewing some of those topics that I think are going to be really relevant. The first place that I'm going to start is going back to the first project on the autopilot in Tesla. Um, I'm going to review the object detection model that we worked on not too long ago, that was recent in our deep learning journey. Um, I'm going to go back and take a look at that. So let me pull that up. That would be within, I think, lesson 9 of our deep learning course. So let me pull that up. Sorry, lesson 9 was transfer learning. It's lesson 10. Let me share my screen here. Okay, so this for the first project is going to be a really fantastic resource. Object detection with YOLO. We did this a while ago, but I do just want to briefly walk back through it as a really good resource for that first project because obviously, um, in the beginning of it, the first part of it is building an object detection model. So the idea there is you should be able to follow this notebook mostly all the way through. It's just you're going to be working with different data, obviously, with the Tesla vehicle data set. Um, so let's go back through this. So remember, we had to do some work here with the YOLO repository, and we use some of those built-in scripts to do the training and the evaluation. So, and we had some helper functions along the way. So we had this function to download a bunch of data. Now, will we need to do that for this for the project? No, because you'll already have the data. So we won't need to go out and download it. So you won't need a function like this necessarily, which was used for retrieving data from the internet. So we didn't really need to do that, which was pulling from this, public data set. You will already have data. But what's nice is like if you want to use it in this format, or with this kind of setup, you want to make sure that the data from the data set is in this kind of format. So you want to have it in an images, you want an images folder. You'll want a labels folder that has these text files. And remember, these text files are unique in that they have the box coordinates on each line, along with the class of what vehicle it is. So we want all of that to be now that should already be set up for you, but you just want to double check it's kind of in this kind of folder setup where you have an overall folder with an images subfolder, a label subfolder, and they have the images are within this one, and then the label files are within this one. We won't be downloading it from a location. We'll already have it. That's just the difference there, right? Um, so you'll already have it from the data sets. Okay. Otherwise, we cloned the model. So we cloned the model from this repository because unfortunately it's not one of those that are built into Keras or built into scikit-learn or something like that. So we're pulling it from this repository so we can use it. So we did that. We set up a results directory to save our training artifacts. So that's something that we still would use in this setup. This is just setting up a folder to save the results to for training. Um, and then essentially what we're leaning on here is this training script. So this is a Python script that is using um, a training loop. And remember when we looked at PyTorch, usually that's a very manually coded out loop, right? It's because in PyTorch, your training is a little bit more explicit, right? It's not just model.fit, which we see in TensorFlow. But this YOLO model is a PyTorch model, so the code to do that training is within this training.py script. And we're going to run that here um, using the existing model, but we're going to train it against our um, data that's set up that's in the right folder, right? In the it's assumed to be in this setup that we talked about earlier with this directory. Um, and then we will uh, execute this. So this, what you want to make sure if you're following this example is you want to make sure this part runs. Um, when you download when you clone this repository, you may, if it's not working for you, you may need to tweak this data.yaml to point to the right folder where you have your data set up in on your machine. So if you're doing it locally, or if you're doing it in Colab, you just want to make sure that you have your data set up. Want to make sure you have this. This is just a configuration to say where on my machine is the data stored. So you just want to look in that file and make sure it's pointing at the right location so it can pick up your data set. And you can also play around with how many epics it's running. So, and what I would recommend too is using a GPU, especially if you're on Colab, connect to the GPU, and this should speed it up. Ideally, right? It should speed it up. Okay. Then we had a helper function to visualize some of our results. So this should be exactly how it is. It's going to look inside of our path and pull in some images from our training run, and then we can visualize what some of our results will be. This is a helper function to do that from our results directory. Data.yaml will be no, what I'm saying is in this is a file that has that. So let me run this actually to show you what I mean. It may help to just run through this real quick. And I don't need to be connected to, I'll just connect to the CPU to do this. So data.yaml is a configuration file that should have a default directory. What I'm saying is if this training isn't working for you, you may need to change some of the configuration settings in that YAML file. I want to see what it actually contains, what it's pointing at initially. So let me go down and just clone this. So this file, if you look at it here, it's just pointing to, so it has some metadata about the data set. So this is what I'm saying is you may need to change this location. This is telling it where to look for the training data, which is inside of a folder that is set up to be, so dot dot means go back a directory, and it's inside of a folder called train, and then there's a folder within that called images. Um, so this might change depending on, like, if you're running this locally on your own machine, this might be a different directory. It depends on where you're saving your data set. Um, but what I would recommend is trying to follow this example as closely as possible, which means that so notice how the YOLO, the data is within a train and validation folder that is underneath the YOLO directory. So once you clone the YOLO directory, you can copy all the data in there in these folders, which should line up to this exact configuration. You shouldn't need to change any of this. Notice, like, now these might change as well. In fact, these are likely to change, which are going to be your labels for the different vehicle types. So, um, these are going to be different vehicle types and you should be able to get that from the label files themselves. You should be able to see what the classes are for the various images. It should be in the dataset description too, I think. Okay. All right, so then if we're following this, it should mostly follow this example. We have a helper function to do inference, so this is to make predictions, which should mostly lean on running this detect.py script, which is, the script that basically does forward propagation for us with the PyTorch model, using our training results to load in the model. Um, and then it's going to store the prediction results inside of this directory. And remember, the prediction results are interesting for object detection, right? They are the box plus the label of what's inside the box, right? And so for a single image, we may have multiple boxes. That's totally possible. So the predictions are not just a label, but boxes with labels, right? And here's a helper function to visualize some of the results. And again, this is something we want to do, and the project even asks you to do, is to visualize some of the detections. Um, and so this is going to run some inference and ultimately visualize it. Uh, and so we can see what some of the images are with those boxes. So this is some examples we saw earlier. But as long as you mostly follow this example, you should be good. It should follow mostly this. The only difference really is instead of downloading this public data set, you're going to be using the one that is given to you with the project, right? And so you just want to make sure that is set up in the right place for the training to work and the predictions to work. But it should follow mostly this example. Okay. So this is a great resource, this 10.07 notebook. If you plan on doing that first project, this is a very, very good resource for you to work with there. All right. Any questions on this? Okay. So that being said, um, let me go over to some transfer learning practice, which I think will help with the second project. So inside of lesson 9, we did transfer learning, and we had a notebook there to practice doing transfer learning. So let me share my screen and show you that one. So this will be really, really helpful for the second project. So this is within lesson 9 of the deep learning course, and this was the only notebook in there, 9.04. This would be a really fantastic example to follow for that second project. Remember, what you're doing there is predicting the various structure images and categorizing them into one of those structures, like the statue or the stained glass or whatever it is, right? The different tourism structures. So the reason this is so relevant is because it's going to walk you through using a model off the shelf, which I highly recommend for that second project, and then just training it against that data that you have with the which are going to be those images. And so this example uses VGG16, which you're welcome to use as well. So here we import this in order to use it. And remember, this was the key was this is what makes everything work is loading in that model here, but making sure we turn off that top of the network by making sure we do include top equals false. Um, which will basically leave out the end of the network so that it allows us to put in our own layers there to do the classification. So essentially, this is going to be our starting point, and then we take this and we go ahead and flatten this result from that last layer of the VGG16, and then we put in a dense here with a ReLU, and then we put in a dense here with a softmax. And again, this number of neurons here should match to how many categories we have for that project, right? So if I go back to that project, um, in part one, there were these categories, right? Altar, apps, bell tower, column, dome, two different types of domes, flying buttress, gargoyle, stained glass, vault. So I should have as many, categories there as many neurons in that last layer as I have categories here, which are in these different folders, right? Um, so we want that to match that number as far as our output. And one of the things that it wanted us to do as well was add in a dropout layer. So that would be worthwhile doing is, putting that in here, and we could drop out right here after this to affect some of these neurons being turned off. Um, so that's something we definitely could do. Um, but once we do that, we see we have all of the VGG16 layers, populated in here, which are all these blocks of convolutions and max pooling, convolution, max pooling, and all that. And then basically here's our final layers we added in. And then we want to train this on the data, right, itself. So this we would want to do these kind of steps to then go ahead and set up our training and go ahead and set up our model.fit and all of that. So, um, that would be something worthwhile doing is basically looking at this example as a good way of setting our network up. And then what we could do is look at other examples that we had for, um, you know, doing the training process, especially with image data. So that may be something worthwhile to look at, and I can do that. Let me find, well, before I find another example, especially with setting up the data loading, which I think will be relevant. Um, any questions on this? So like this is what you'd want to be doing for this second project, that part one, right? Is using transfer learning to your advantage. And really what it's doing is building your model for you, right? It's just building your model for you. You still have to do everything else. You still have to get it ready for training by doing model.compile, and you still have to actually train it by doing model.fit. You're still doing that, but this is giving you your model architecture, right? Is you're pulling this off the shelf and then adding in a few layers at the end to do the classification. We practice that a little bit. This is a great resource for setting that up. Um, any questions on this? Again, really great resource for the second project. Uh, this is a good example that you could follow on using one off the shelf. We actually have multiple examples, I think. I think we have one later on uh, um, of using transfer learning as well. All right, so let me find, I actually have another example in mind that I wanted to use. Let me see if I can find it, which has it's the roses. And remember we loaded those like rose data sets so we could, yes, this one, as a good, just to show you like a good way of uh, setting up the data here. So let me share my screen. It's this one. So this is an 8.08. The reason I think this is a good resource for that second project is you should be following the way this loads in the data, because the data that you're going to have, remember, is set up in these folders. So go back here, it's set up in these folders like this. And this will assume a similar setup. So this is a really good resource for examples on how to load in the data set for working with Keras and TensorFlow. So remember, we download the data set here. And what we did is we basically used a function. If I keep going here, by the way, this is a helper function to just display images. Um, so this displays an image given the directory. So that's a helpful example. This is what I really wanted to show off was for that transfer learning example, when you're training, this is how you want to load in your data, exactly like this. So you want to use this utility image data set from directory because our images are already organized into these folders, right, with the labels. And this function assumes that structure. And so we can pass in the directory path and basically, this will read from those folders and organize them into their classes, right? So you can see how many classes there are. Um, and you get this confirmation that it found all these files belonging to 5 different classes. And you can set up how much data you want to reserve for testing, and it will split that out. And so it reserves a certain amount of them for training, and then it reserves the remainder of them to be used for validation. So really excellent reference here for how to load data from that kind of folder setup, which I think you would want to do for building out your training set and validation set. And then you can visualize. By the way, you can also get the class names from the this class names attribute. So once you've loaded in from those folders, you can grab the class names from here and you can see like you should have all those names that match this. You should have all those exact names that match your folders. Um, and so that's how you can verify that it loaded those correctly. This is a really good function because in the project instructions it wants you to plot some of the example images. This is a really good example to grab a batch and go ahead and plot them. So it uses the PLT imshow function to plot, and then it puts a title on it with the label, right? So you grab the label of the image, and which is an index, and you use that index into the class names list to grab the string. Uh, and so that puts it on the title. And so this is a really good way to kind of sample visualize some of these images in this subplot. So it plots the first 9 images. Obviously, you can do more than that. You could build out 20. You could do however many you want to do, but um, 9 is a nice number because it's this 3 by 3 grid of images. Yes. Yeah, it was organized. Yeah, so in this situation, it's organized like this where there's like a data set directory here, and underneath of that are the folders with each type of flower. Yeah. So we had each one of those. So when you like this data set's going to be organized very similarly, right? It's going to be a folder that has a bunch of subfolders that represent each class. So images of altars, images of bell towers, images of columns, images of stained glass, right? It's going to be set up in the same exact setup. That's why I think this is a good, uh, very good example of how to load in a training set and validation set given this directory setup. So when you specifically have that directory set up, this helper function can grab that data for you. Yeah, which I recommend doing. So I think for that part one of the second project, I think you're going to want to lean on this as a good example of loading the data. And not only loading the data, but training a model, right? So now, obviously, in this one, I think we built our own convolutional net. Um, but this also, by the way, has a really, really fantastic example of adding in augmentations, which we did not do on the VGG16, but something we certainly could do. So what the project wants you to do is set up training it with and without this added into the model. So there's no reason we can't take the existing one and in the very front of it build a sequential that has this first with some flips, rotations, and zooms added in there. Um, and we can put this first and then have the rest of our model second um, in the sequential, right? Because you're allowed, remember in Keras, you're allowed to put a sequential within a sequential. So you can, so this is a good example of that, where you put this augmentation first and then the rest of the architecture. And now this is a custom model that we did ourselves, but there's no reason we would just use our transfer learning here rather than having a very custom architecture like this. The rest of this model is basically going to be the one we already built with the VGG16 and our custom layers at the end. The only thing we're really adding to it is this augmentation. This is a good example of that. And then we summarized it, we compiled it. So this should look very similar. Using Atom, using accuracy, using cross entropy. Now, remember, this one did not have a softmax, right? It doesn't, so it does not have a softmax here. So therefore we had to turn this on to true. But the default behavior would be to have a softmax, and then we can leave this out or just set it to false, which is the default. So that's the only change from this example of the compile. Which if I go back to this, we added, here, um, you could just use this, which by default assumes we have a softmax. You could just use the string. So that's the only thing that would really change. And then we do model.fit, right? Model.fit. We pass in our data set, we pass in our validation data, and we can change the epochs, etc. This is another one where I would recommend using the GPU if you're in Colab, because anytime you're doing these vision kind of tasks, right? I think uh, using the GPU is going to be beneficial. Okay. All right. Then, given an image, we can always predict on it. So we can do model.predict on a batch of images too from our test set to kind of validate our predictions. So that's, something else we could do. All right. So this combined with this should be enough to get you going on that second project on the first part. I think those are really good examples that you would want to follow, especially with augmentation and the augmentation and the VGG16 example in the 9.0 for a notebook. The only thing that we do not have here an example of is the early stopping. So if you want to add that to the mix, you certainly can. So remember that would be doing something like this, where you build a callback, which looks like this, where you monitor some metric, you do the TF Keras callbacks early stopping, and then inside of the fit, you just add that callback, right? So callbacks is early stopping. So that's just a simple addition. I forget exactly which notebooks we had this example in, but we've done that before. I think the project asks you to do this too, is add in early stopping. Um, but that's really simple to add, right? Really, really simple is just setting up an early stopping callback and then making sure you put this in here in the model.fit inside of this callbacks list. Um, the other thing you could do, you're not required to, but maybe, if you want to practice it, it may be worthwhile, is setting up TensorBoard, right? We talked about setting up a TensorBoard callback, and then you can put that here in the callbacks, and then launching the TensorBoard, um, launching the TensorBoard extension inside of the notebook and visualizing the training. You don't have to do that, but if you're interested in it and you're doing a lot of epics, it's usually valuable to see that, which I think will be a good example for, again, that second project. You're going to be doing item-based collaborative filtering. So we have a really good example of that here, which you uh, would be following. All right, welcome back in. So what I was saying is I wanted to resume here by walking through an item-based collaborative filtering example, um, which will be really helpful for that second project, right? Because that's the second part of it is building out an item-based recommendation system. Uh, so I'll walk through that example here. That's going to be a little bit down in the 7.01 notebook um, under this section called item-based collaborative filtering. This will be a really good resource for that, and we'll walk through it together. So if you remember, one of our goals here with the collaborative filtering is to essentially figure out what items are similar to another. And the way we do that is through their ratings profile, essentially, right? Like what items gathered similar ratings from users, which we will calculate through this cosine similarity function. If you remember, we use that. Um, and remember what that does, just conceptually, is it looks at the angle between the two ratings vectors. Any two ratings vectors in the matrix, we can look at the similarity between. And so remember the visual idea of that is like if two ratings vectors are very similar, that means they have a very small angle between them, and ones that are exactly similar would be right on top of each other. So they basically would have a cosine similarity of one, meaning their angle would be very, very small between them. But if they're dissimilar, meaning they're much different ratings vectors, they're going to be wide angled here and very far apart, which would drive their similarity lower. So the similarity metric is between 0 to 1. And this very wide angle would be closer to a zero similarity. A very small angle, meaning that the vectors are very close to each other, would be a high similarity, so closer to 1. And so that's going to be our primary metric for determining which items are similar to each other, right? Is through their ratings data. Um, and so we will see that. Hopefully that rings a bell. Um, when are the projects due? It should be Uh, ideally, what you want to aim for is what we've always done is like 2 weeks after the last lesson, which will be on Monday. But uh, realistically, you have until the end of your program to submit it in practice because that's how long it'll be open for. So, which you should be able to find that date, in your LMS, like how much time you have left in your course. Uh, but you want to try to do it in a reasonable amount of time, right? Um, and I think these projects will be very, very doable, especially because you have some really good examples to follow. I don't think they'll take that long. But yeah, a good goal is like 2 weeks after Monday, 2 weeks from this upcoming Monday. Okay. Okay, so walking through this example just to see it again, there's a fake data set with items, users giving ratings to various items. Uh, Obviously, in the project, you have a real data set that has users and items and ratings in a CSV, right? So you have the user ID, you have the item, or in that case, the item is a location, right? You have a place ID and you have the various ratings of those places. But we have kind of a fake data set here. Um, let's run this. So, but you have something very similar to this that you can load into a data frame from the CSV, uh, um, that you start out with in the project. So we have this dictionary, and then we can load that into a data frame. And so what we have is this data frame here. Um, Thank you. Yeah, so if you have that data, you'll basically load it into a data frame. So this is the kind of data that we have in this user item setup, right? So the columns are the users and the items are on the rows. This is the setup that you want to have. Now, when you load your data into the data frame from the data set, it won't look like this necessarily. You're actually going to have various columns. And so what you need to do to get this kind of matrix is you need to pivot it, right? You need to pivot that data set. There's actually an example of doing that, I think, earlier. If I scroll up here, um, on the anime data set for this user-based collaborative filtering, I just want to see. Um, Yeah, so this is the one you would want to follow uh to kind of pivot that initial ratings CSV. You want to pivot it. Now you what you actually want is the transpose of this because you in the item-based collaborative filtering, you actually want your rows to be your items. So you do want to use the pivot table to generate your matrix, your data frame, but you want your place IDs to be on your index and you want your user IDs to be in the columns, and then the values are the ratings. And so you should end up with a basically a matrix that looks like this, but transposed, right? Your places are going to be here on your rows, and your users are going to be here in the columns. So that's what you want, which is exactly this setup in the item based. So notice the item based has this data frame that has the places or the products, the items are on the column, or sorry, on the rows, um, and the users are here on the columns. And so when you do that pivot table, you're going to have null values naturally because not every user has given a rating to every place. So you're definitely going to have null values, which is very, very common in recommendation. And that's okay. You can leave it null because that's fine. Usually, when you build the recommendation system, you're going to end up filtering those out anyway by looking at the places that they've actually both all the users have given ratings to, and then using that vector to do the similarity. So when you're doing your example, you're going to load in your data. You want to pivot table it so it ends up in a setup like this. So just something to keep in mind for that project, right? Pivot table to keep it like that. Okay. So then we have a helper function to grab all the unique items. Um, that's just so we know what all the unique place IDs are. This is just a helper. So we have that list of unique place IDs just for reference. So we can have those. So these are all our unique items from the data set. So we should be able to grab those. Okay. Now, here is a really critical function that we would want to build, which calculates the similarity between any two items. Now, it's going to be really important because remember what we're going to do is essentially um, given any item, we're going to go through and try out every other item here and figure out what are the most similar ones. So we'll always have one to start with, which is our given place, our given tourism location. And then we'll basically cycle through every other potential location and generate a similarity. And filter out to the top 10, top 5, whatever for our recommendation. That's going to be the strategy for the recommendation, right? But in order to generate that similarity, remember we have this function. And one of the things that we do is this initial filtering to given these two items that we're checking their similarity between. is to go through and find ones that both have ratings, right? So we want to make sure both of those have ratings across our users. This just eliminates eliminates the places where one of them doesn't have a rating, because then we won't be able to compute the similarity. So essentially, this iterates through every user and checks, did the user rate both items? So if they did, we add both of those ratings to this dictionary, so that we have every instance where a user rated both of those items, right? Every single row where both of those were rated, right? So that's all we're doing here. And then essentially what we're doing is, if there were no overlaps, meaning there were no cases where both of those items were rated, we basically return zero, meaning there's absolutely no similarity we can compute, no similarity. That's basically we have nothing to compare because there were no instances where two users gave ratings to both. That's probably unlikely to happen, but in the event that it does, we just return a default value of zero similarity, right? So that's just this case. Very rare case, but it could happen. Now, essentially what we want to do is grab all of those ratings that were from item one and item two by the common users. So users that gave ratings to both. And so we collect all of item one ratings and all of item two ratings across those users that rated both. And so we end up with these two vectors, item one ratings and item two ratings, and we compute their similarity through the cosine similarity function of those ratings vectors. So that gives us the similarity, which is a value between 0 and 1 of these two items. So remember the logic there. Given two items, let's look at all the places where users rated both, collect all those ratings, and compare those two ratings profiles to see how similar they are, right? Okay. So that's this function. So essentially, you would be using this exact function to compute item similarity. Um, so pretty much that. And we can test it here by looking at the similarity between the Dexter show and the Mr. Robot show. And again, like in the project, the items are places. So we could use a place ID. So place ID 1 and place ID 10, which are two different tourist locations. um, we can compute the similarity. All right. So that function will be really critical in actually doing the recommendation. So this function here is basically what will give us our top N items, however many we want to do, in terms of our similarity. So essentially what we're going to do here is, given an initial item, so that's called the target item. So given that initial place, which is exactly what we want to do in the recommendation system, is given a place to start at, let's go through and for all the unique places, let's iterate through and compute the similarity across every unique place that is not our target. So this is looking at every other place. How similar is it to our starting item, our starting place? Right, that's exactly what this code is doing. And it's generating this scores list, which is examining that similarity score between every other target item and our starting target item. And so what we can do with that is, obviously we can sort this according to our greatest to least similarity. And so that's what this does. It sorts it in descending order. And what we can do is, and I would recommend doing this, is we can also put in a parameter k, which could be, defaulted to 5, for instance. But essentially, what we want to do is return the scores up to the top K scores. So something like that, which would return like the top five, or if we change that to top 10, top three, that would be a more realistic kind of function, right? Is give us the top five, top three, not the entire list of scores, because that's not going to be that useful. From a recommendation perspective, usually, the top five, top 10 are usually perfect. Um, so that would we can put in a parameter K and we'll get only the top K scores there from that list, which is what that would do. Okay, so then we can test that. So given a starting item, this gives us the similarity across all the other items. And obviously we could pass in the parameter uh, um, top three, which would limit that to the top three. So if we generate this function, run that, and then we run this, and then have this function and generate this. So this is only giving us the top three. Right? It's not giving us the list on the entire, every single similarity. It's just giving us the top three that we might recommend, given a starting place ID that's in our data, right? Given that, then we can recommend the top three similarities. Okay. Now, the reason we don't need this was also in this demo. The reason we don't need this is because we're not given a target user. If we were given a starting user, we could filter to essentially the ones that they haven't seen before, and recommend ones that they haven't seen. But we're not, that's not what we want to do in the project. The project is all about, given a starting place, what are other places that we could recommend? And that's what this would do. So in the project, the adjustments that you need to make are, you're mostly going to follow this exact example. The adjustments that you would want to make are, when you load that data from the CSV, you're going to want to use the pivot table, like what is used up above that I showed earlier, to initially load your data into the user item matrix, which is going to be that ratings data set. You want to load that one into a data frame, and you're going to want to pivot table it, but you're going to want these flip-flopped. You're going to want the place ID as the index because you want that to be your rows, and you're going to want the columns to be the user IDs, right? So you're going to want this transposed. And so you could load it exactly like this and then transpose it. That would work too, but you might as well just save yourself, that one extra operation by just ensuring that when you pivot table this, the index is the place ID, right? It's the tourism location should be on the rows. Okay. So you're gonna do that and then mostly follow up with the with the item-based collaborative filtering example. So this should be a really great resource for that second part of the second project. Really, really good resource here. Any questions on this one? I know it's been a while since we did a recommendation, but hopefully that rings some bells for us and seems somewhat familiar. All coming back. Okay, great, fantastic. Okay, so a couple more examples I wanted to run through that are going to be especially relevant for the third project. So again, for the second one, the resources that are going to be helpful are the 9.04 notebook for transfer learning and the 8.07 one for looking at the loading of the data and the augmentation part of the neural net training. And then this recommendation system one, that those resources should really help you for that second project. For the third one, what I want to do is look at a couple of data frame operations that I think are going to be really beneficial. The first one is going to be in this. This is all the way back in our data science course in lesson 10. So in lesson 10 on feature engineering, we had this 10.01 notebook, which I think will be a good resource for that project. The third one on sales forecasting just because it has some good examples on grouping, right? And I think you'll find yourself doing group by operations, or at least you should be in a bunch of those data analysis tasks in the first part of that project. So I just wanted to review the group by operation just to see some examples of it. Um, so in this, so I'm in the 10.01 notebook, but I'm scroll down a little bit to this section 8 here of the notebook, and it goes through a an example with some fake data here. So we have this fake data with different a column for the category of product and then the revenue from those different products. Um, and I just wanted to show off some of the group by examples. So when we load this data, we initially get this data frame, and one of the operations we can do is this simple group by operation, which allows us to group according to a column or even multiple columns if we want to. And so this is a good example of grouping by this categorical feature. So this groups by the this category column, which is going to look at the the category and look at all the rows for each of these unique values in that column, right? So it's going to look at all the rows where we had the electronics, all the rows where we have clothing, and then do something with that. So you're going to have some aggregation that usually follows the group by. In this situation, we only care about the revenue column. So obviously that's the only one there is, but um, there could be other columns there that we aggregate. In this case, we're only aggregating the revenue. But in the project, this may be the sales column, right? That sales column that we generate from multiplying the price times the quantity, and we generate a sales amount. And so, for example, like we could take the sales and total it per category. That's what this is doing. It's kind of how you read this group by, right? Is you take the sum of the revenue column per category. So what that's going to look like is it's going to take each entry that's underneath the electronics category and add those together because that's what our aggregation is. But obviously, that math could change depending on what aggregation you put there. So you have a lot of options. You can do things like mean, which would average all those entries per category. You could do median, take the median across all those. You could take the min or the max. You could take the count, which would give you how many records there are per, or how many rows there are per category, which is essentially like a value count. Basically, is exactly what that would be doing. So how many rows do we have where we have electronics category? How many rows do we have that have clothing? That would be if we had count here would be the equivalent of that. And there are use cases for count. Actually, in the first project with the Tesla data, I would recommend using this kind of group by to count um, how many rows there were with the driver as the victim, or how many rows there were with the cyclist or pedestrian that was in the accident. So these kind of group bys can actually be really useful. Um, but in this situation, like the total sales uh, per this column is a really useful really useful aggregation. By the way, this part of it here is an important part in the sense that what it does, like if we didn't have this, and I'll show you the effect of that actually. Let me just show you the effect of not having this. So if we don't have this, every time you do a group by, it puts your whatever you're grouping by as the index by default. So essentially what we're going to get is a new data frame that has this as the index, like each unique category as the index, and then the column is going to be this aggregation of the revenue. So let's see that. If I run this code, we're going to look at the original data frame and then the grouped data frame. We can see the difference of those two. And without that reset index, um, rerun that. Without the reset index, you can see we get this data frame. Now look at the index of this last data frame. It's the index is the category, which is either clothing or electronics. But that may be okay for some of our use cases. Um, but this is now the index. It's not its own column, and it may be desirable to have that as its own column so we can do things like filtering, right? Um, but one of the things that we can see is it definitely aggregated properly, right? So this got totaled for the clothing was 300 plus 400, which is 700. That makes sense. That's the sum. But obviously we can see how that might change if I put in max. If I looked at the max there, that's going to take for the clothing category, that was 400 because that's the max. And then across the electronics, the max is 700. So obviously the aggregation there matters. But for the sales, um, the sum is likely what we're going to want is the total uh, per day. So when we group by, the what are we grouping by is generally going to be the day, but not always the day. It could even be the store. So one of the suggestions is, or one of the things we want to do in the tasks is group by the store to figure out what is the revenue per store. Um, the other thing we could do is group by multiple categories. So in that project, it may be in that third project, it may be desirable to group by multiple things. If you want to group by multiple things, you just have to put it in a list. So for instance, there may be something like this where we want to group by store and then group by day and take the total across the sale. So we should have a value per store per day and have a total, which may be desirable to, then we can aggregate that even further. Like we can resample it, which I'll show us how to do in a moment. Um, but that may be something we want to do, right? Per store, per day. Um, but what I want to show you too is the difference. So if we run that reset index, what does that do? So if we run the reset index, what that's going to do is take this and move it out to a column. So that's what reset index always does, is it takes your index, puts it over into a column, and then resets the index to be the default numerical index. So what's going to happen is we're going to end up with a new column called category, and then we're going to end up with a default index of 0 and 1, which are just the row index, right? So when we run reset index here, that's going to produce our group by. But notice how we now have a default index of 0, 1, but we have a new column. And you may wonder, why do we care about doing that? It's because we can do things like this now with the reset index, right? This will now work where I can actually filter according to this column, right? I can filter according to this column and I could even group by that further, like in the case where we're grouping by date and store. If I make that a column, I can then further group by the date and resample according to that date and etc. Right? So it's useful to have often when we produce our groups, it's useful to have that as its own column. So these are our unique groups here. Um, and so all you have to do is the reset index here will kick that out into a into its own dedicated column. Okay. We have some more. So in the data frame, so I think earlier in this data frame we loaded housing price data and we grouped by the city and averaged the price per city. So that's exactly what this is doing, is just grouping by city and taking the price column and averaging it. So obviously what we could do is do different aggregations there. Like if we wanted to ask different questions, like what is the max price per city? Like in the project, I think you are doing the max price per store for an item. You would replace this, you would group by the store and look at the cost and do the max, right? So it would be something like group by store ID and then look at the uh, um, cost or look at the price. I think that's what the name of the column is the price, and then take something like the max, which would be the maximum price per store. So that's something we could do, right? Just as an example. So grouping by really, really powerful, and it's something that is used for analysis all the time to generate different aggregations across different columns. So in that third project, you'll do a bunch of different group buys. So this would be another one. Average price per city, and we can sort that too. So anytime you need to produce like a list of the top values, you can sort that according to, remember the syntax. Oops, remember the syntax for sort is to for a data frame is to sort values, and you pick a column. So this by argument is the column you want to sort by, and then you can put ascending to false to get a greatest to least sort. So the default is the least to greatest, which is ascending equals true default. So you have to turn that off to greatest to least there. That's what that does. So this was the city max. So every city we got the max price. This was the minimum per city. This was the average per city. So this is all the housing price data, right? We just did some group by examples of it. Here's some good examples. And then we just extracted with this iris data set. And I also recommend, it may be valuable to go back and look at some of these plot examples from lesson 5 um, within our data science course if you want some more examples of doing visualization, because visualization can be really helpful to, see the histograms or see, um, you know, uh, um, different plots like a box plot uh, to kind of visually tell us the story that we're looking at in terms of trends uh, or patterns or those kind of things. Okay. All right, so this is a good resource for that third project. This lesson 10 demo from the data science course. Any questions about the group by operation? It's been a while since I've done it, but there's some examples. Hopefully, it makes sense what it's doing. And, if you're familiar with querying data like in a SQL structure, it's literally the same thing. It's the same as doing like a group by and a query. You think of this data frame as like a table. Um, that's all it's doing is just processing this aggregation that we would be doing in like a select statement where we're grouping by this um, column. in the table. Okay. So there is the group by example. I wanted to show one more that I think would be helpful for the third project, which is going to be resampling. So this is over in the 4.03 notebook in the data science course as well. So another good resource for that third project, besides that lesson 10 notebook, is this 4.03 notebook. Because it has a section on resampling time series data, which is exactly the kind of thing that you want to do for that third project, right? Is you have daily sales values and you want the ability to roll that up into quarterly, yearly, monthly, weekly, those different frequencies. And it turns out it's really, really easy to do. Um, the only catch to using resample is the date has to be the index. And so it may not be the index, in which case if it's not, you can easily make it the index by running an operation like this on the data frame that you have, which will set the index. Now, the alternative to running set index, if you group by date and return a result from that, it will automatically make the date. If you don't reset index, it'll make the date the index, right? If you imagine so if you had a data frame that was and you did df.group by and you group by a date, and then you did then you looked at the column and you did the sum. Uh, this will this here the data frame result is grouped by date. And so, but this would make it that the date is the index, right? So this would make it this result df. This data frame would have the index would be the date. But because remember, if you're not resetting it, whatever you group by, so that's one way to get it that way. The other is to manually force the index to be the date by running this operation in case you can reset it. And you have date column, you can always make it that. Now, why is that relevant? It's because the date needs to be the index one way or the other so that we can run this resample function. So on a data frame, on any number of columns that you want to, you can run this resample, which is essentially a group by at different time frequencies. So different grouping time frequency. Remember, you can switch over to be whatever frequency you want. So you can put in month, you put in week, you can put in year, you can put in quarter. Um, and that will basically roll your up to those frequencies and do some type of aggregation. So maybe you want to do your average sales per quarter, you would use mean, right? Or maybe you want to look at your max sales per quarter, you would use max. Or you want to look at total per quarter, you would look some. And obviously, you can choose to do different there. So maybe mean, um, and maybe you would do that at the year level or weekly level, whatever that is. But it's at least a operation is to run this resample, and then you can do some aggregation off of that, like an average, a max, a sum, a count, whatever that is. But so really straightforward. It's pretty easy to use. Is this resample function? You use that anytime you want to take your dates and roll them up into some aggregation. Like you want to take daily data, is what you have for sales, you group by date, um, and you want to get like a weekly average or a weekly total. And so what that's going to do is give you a new data frame that has index by the week and then give you the aggregation of that result, like the total or the average or the max or min or whatever it is. Group by provides some count, etc. fields associated with unique combination of values. Yes, that's exactly what it does. Great description. Yes, you're exactly right. It's exactly what group by does. And to some extent, resample does the same thing. It's just oriented towards time-based fields like a date, right? It's really oriented towards that and an hourly level for a single day. So we had all this hourly level data with whatever fake values are here. Um, and what we can do is resample that to a day. So because this data is at a lower frequency, right? It's per hour, but maybe I don't care about all the data at the per hour level. I just want to know like what is the average of this across the day, or what is the total of this across the day, in which case I can resample to a day. What that's going to do is collapse all of these down to a single value for the day. And then it's just a matter of what am I producing? Am I getting a total? Am I getting an average? How am I reducing that frequency? So in this situation, we were reducing to the sum. So we resample and we take the sum, I believe, which totaled this up across the day and returned a single value for that day. So look at what the new index is. It's now a day. I don't care about the data at the hourly level. I've just rolled that up into a single day and taken the total. But obviously, we could take the mean or the max or the min or whatever and get a single value for this and this for this day. And the same thing works like if we had all this data at a daily level, we could get an average for the month or a total for the month, right? And that's what you want to do in that third project is really, um, generate different quantities uh, uh, per different time frequencies like quarter, year, month, etc. So this is the reason I wanted to bring this one up is it's another good example for that third project of building a model off of this data. So this was our bike rental data set. We did a capstone session demo with this together, and this one also had a similar kind of style to it as that third project of building some type of model, but at an hourly level, right? To predict the rented bike count as a regression problem. So this is a really good resource as well for the third project because you're doing something similar. You're trying to make a prediction at a yearly level. Here we're making a prediction at an hourly level across these different dates. Um, so this was a really good one that walked through all of that, like looking at converting our dates to date time objects, which we did, and then generating some features like day of the week, which comes from this date time, um, the DT attribute. And that's something the third project I think also asked you to do, right? Is generate a feature like day of the week, day of the month, um, what month of the year is it? So those kind of features. Here we generated a weekend feature, which was looking at day of the week if it's greater than or equal to 5, which means it would be Saturday, Sunday, which would be 5 or 6 for the index. And so we had a weekend feature, and we looked at some of these in the correlation. We looked at some of the counts. Most of them were piled up here in the like 250, like 0 to 250 range were most of them, but there were some days where it was pretty big out here to the right. So it's an interesting histogram of that. This is a really cool plot here. Remember, we have seen this before with Seaborn, the pair plot, which plots like remember what it does is it plots a scatter plot of every feature against every other feature. And then on the diagonals, because if it doesn't make sense to plot a feature against itself, it does a histogram right on the diagonal. This was a really cool plot of all of this data here. So that's usually a cool a cool visual. So then we started going towards our model, and in this situation, we actually didn't need to really roll it up to any other frequency because we just looked at the count. Um, we just looked at the count and some of the other as our target, right? The count because it already was at an hourly level, and that's what we were predicting it at. But the extension to this would be like if I wanted to predict it at a daily level, we could aggregate this further, right? So like we have an hour per day. We could group this by the day and take the total, which would generate like a total amount of bikes per day. And then we could resample that to give us like a total per month or per week, right? And then we could make predictions like that. So even though this data is already set up in the way we want to make predictions is like per hour, it's already set up that way. And so we can just build the regression, which is exactly what we did. We built the regression by just using all the features and using the target. And what we did is we train test split it. And then we actually built a pipeline where we did the standard scaling to all the numerical features, which is what you would want to do if you're building a regression. Definitely want to, standard scale all those features. And then if you're any categorical features, we one hot encode. And then we have our pipeline, which does that with a linear regression. And obviously, we could swap out that linear regression for other kinds of models, like a random forest regressor, uh, which is what you want to do in the project. So this is a good um, this is a cool, yeah, this is a cool demo or capstone that is really relevant to that third project. Like I said, the thing that you want to do is aggregate. You will have to transform the data to get it to be in the different time periods that you need for the prediction. So luckily for us, this data already was set up in the hourly, which is like this is what we wanted to predict was the hourly level of rentals. But as I said earlier, there's nothing stopping us that could group by this date and total this up per day, right? And then we could predict at a daily level. And then we could even resample that day to predict at a weekly level or a monthly level or a yearly level. Hopefully that makes sense, right? It's not too hard to extend this to that kind of prediction. Um, Here, it's just doing it at an hour by hour basis. So we are predicting that, but obviously we could like total this up across the day um, if we wanted to. So we could group by the date, aggregate this to a sum, and then resample that date to a week, month, quarter, year. I think you would end up doing all of those in the project. I think what your model is going to be built off of, though, is the yearly values. So you would roll this up to a yearly total and then use that to build a model off of, or maybe a monthly one. See what it says. Make a forecast for the next year. I think it's at a potentially at a monthly level though, because you want to use, or maybe at a daily level, you could do that. You could actually just use a daily level and predict the days for the rest of the year. It's kind of what this it's kind of what this is doing, predicting the counts. This X test would have daily values and daily features, and we would be predicting, or I should say, hourly features, and we would be predicting every hour for all the hours that are in this test set, right? Okay, very cool. Any questions on this? So this is a really this is a good resource for the third project, along with that the 4.03 resampling from data science, and then uh, the lesson 10 on the group by from the feature engineering and data science. I wanted to pick up in this lesson kind of at this point of it, which is on page 23, um, talking about various agent frameworks. And the reason this is relevant is because I think it'll be beneficial to see under the hood of how these agents are actually built. So I think we may have some experience working with these things, but um, it's useful to see sort of the elements that go into building them. And there's a few different frameworks in Python that help us build agents and particularly multi-agent systems. So we want to talk about that here. What are those popular libraries that help us build them? There's a bunch in the industry. I'm going to mention a few that are really, really popular. And then we'll spend today doing some examples from a couple of them at least, maybe all of them if we have time. But that's kind of the plan for today. So let me go through this and kind of outline what some of those popular frameworks are, which would be here on this screen. So the three major ones that I want to touch on and do some examples from are LangGraph, AutoGen, and Crew AI. So at a high level, what are these? These are Python libraries that help us build agent systems, right? So think about we have Python libraries to do a lot of AI things. Like we've had TensorFlow, we've had PyTorch, we've had Scikit-learn, we've had Pandas, we've had NumPy. Those all help us manipulate data, build models, build neural networks. These three are additional Python packages that help us build agents and multi-agent systems. So a system where we have multiple agents interacting and collaborating with each other. Um, and so you can build out these workflows or multi-agent systems in these kind of Python libraries, LangGraph, AutoGen, CrewAI. And they all have their differences. So they all have differences in their syntax. They all have differences in what they're kind of suited towards, on what kind of workflow or agent system they're kind of geared towards. But all of these are widely used in the industry to kind of build out agent systems. And so I do want to go through some of the differences of these and then look at some code examples of each one of them if we have enough time today, so that we can get some exposure to how do we build agents, see some of those features of them. Um, I want to start with talking a little bit about LangGraph, and then I'll talk about AutoGen and CrewAI. So, LangGraph is from the makers of LangChain, which is another popular LLM library that helps you build like LLM based chatbots and those kind of applications. Um, and it's an open source library. All of these are open source libraries in Python. And LangGraph is called Lang and Graph because it brings together LLMs in this kind of graph structure, almost like a TensorFlow in some ways, to build out the multi-agent system or the workflow. Um, and so LangGraph utilizes nodes and edges to connect, like a node you can think of as an agent or a function, so doing some type of task. And then you can connect that to some other node, which could be another function or an agent. You can connect those with edges. You can have conditional edges. So essentially, you can build out your workflow, especially if it's very linear and sequential. The LangGraph works really, really nicely to connect. Like I have one function here that passes, it does something, maybe it does like an internet search, pulls in some research, and then passes that to an agent who summarizes it or writes a report or something. And then you can send that on to maybe a document reviewer, reviews the results of that, and then maybe make some edits to it. And then you can kind of pass along the final result of the review. So LangGraph allows you to build an agentic system that's very graph oriented and flows from nodes connected by these edges. And so if we have some time, we'll see how we can build that. But LangGraph is very suited towards agentic workflows that are very sequential in nature or laid out kind of in sequence going from point A to point B to point C. It's not limited to that though. Like there could be situations where we can have conditional edges. So maybe we go from point A to point B or C, depending on a condition. So we do some research, depending on the kind of data we pull back. Maybe we pass that on to a content writer, or maybe we do like another research if we don't pull back the right kind of information. And then those can kind of flow this way, and then they can be we can bring back together the results in kind of a graph like this. So it doesn't need to be completely sequential. No, you can. LangGraph has a lot of flexibility to build many different kinds of graphs, but that's the way that library kind of operates is all graph oriented. So you build out your graph, and then when you run the workflow, you kind of launch the graph, and then the you usually send in a prompt to this first node to say, here's what you want to do, and then this kind of kicks off, does something, passes the result to the next node, that does something, passes the result. And each node could be like a specialized agent or a function. So LangGraph is kind of designed to work like that. Um, and if, again, if we have some time, we'll build out a couple, we'll do some demos with it, build out some examples with it. And I think it'll be pretty cool to see that one in action. Um, so that's one way of approaching building an agentic system is kind of modeling everything on a graph structure. These other two, so AutoGen and CrewAI, don't really do that. They actually they both model a multi-agent system in sort of a team or collaborative fashion. So what AutoGen does is it allows you to build multiple agent objects and then kind of put them together in a team. So you have an agent and then you have maybe another agent and then they conversate with each other. So you can build agent objects and then kind of put them together inside of what's called a group chat structure. And they pass ideas and collaborate amongst each other. So you may have like a planning agent, and then you can have maybe a writer agent who's writing up an itinerary or something. And they'll work together by having a chat amongst themselves. And that kind of plans out the work that each one will do. And then they'll um, agree, like the planner will go out and find details of the trip, and then the writer will kind of write out the itinerary. But AutoGen works by instantiating agents and then putting them together in kind of a chat structure. That's how AutoGen works. And again, if we have time, we'll do examples of all three of these so you can see the differences. But um, that's very similar to CrewAI, which is the reason it's called CrewAI is because you are doing something similar. You're building agents and putting them together in a crew. So you build an agent and then maybe another agent, um, which are all objects that come from the library. So instantiating agents is really easy. Um, and then you basically put them together in a crew. So you have a crew of agents, and then the crew kind of similar to Autogen kind of conversates together, works together to figure out the planning, what to do, which tools to use, those kind of things, and then goes out and kind of executes the task according to that planning, um, depending on what your initial prompt is. So these two are very, very similar in the sense of building out agents and then having them work together kind of autonomously. LangGraph is a little different in which you are generally supplying the structure of the workflow. And so again, LangGraph tends to be more oriented to building an agentic system that is you have an idea of what the structure is. You know it should go from A to B to C. Um, Whereas Autogen and Cray are kind of just instantiating agents and then having them go out and do things on their own as part of a team or a crew in the case of Crew AI. So again, we'll do examples. I think the very first place that we'll start after we do a little more discussion of these three frameworks is my plan is to do some Crew AI examples, and then we can work our way back to LangGraph and then see if we have some time for Autogen. If we do Cray, a lot of it's going to be similar to if we had done Autogen. They're very similar. But again, these are all open source Python libraries for building agent systems. So they're, very, very popular. And uh, a lot of people will build agent systems in any one of these three. And then there is the possibility to have an agent system that's built in LangGraph actually talk to an agent system that's built in Cray. They can talk through what's known as an agent-to-agent protocol. That's possible. We won't really see that today, but if you're interested in exploring that, that is kind of like MCP we talked about last time, but that's known as A2A protocol, which is very interesting, allowing agents to kind of communicate with each other, even if they're written in different frameworks, which is interesting. Okay. So again, just a high level summary of those. We could spend a lot of time, and if we were in a full, the AGS program, we would spend time on lessons going through each one of these. We're not going to get all that time today, but I hope to establish a couple examples in each of these if we can. So I think it'll be valuable to see how these systems are kind of built, and especially what are the differences between these Python libraries that can help us build these agent systems. That'll be kind of the goal of today. Okay, so let's keep going with some of the differences. So in terms of some of the scaling and optimization, now this stuff we may not be that interested in terms of a lot of this is infrastructure setup. So, depending on if you're doing that part of it, may not be that interesting. It could be another whole nother team managing kind of the infrastructure or DevOps of this. But these libraries are different in the sense of how they are scaled or how they are optimized. So there can be different ways to manage their scaling. Uh, what I really wanted to focus on is how they manage state, which is important. Um, Essentially, so the state management is really important because that enables sharing information from agent to agent or throughout the workflow. You may have a team of several agents, or in LangGraph's case, you may have many nodes, and you need to share information between those nodes, right? In order to pass context from agent to agent to agent. And so each one of these frameworks handles that slightly differently. So in LangGraph, there is a notion of kind of a managed or version state. And it's kind of like a snapshot of all the context that's currently being managed. So again, if we do a LangGraph example, we will see explicitly that state object kind of being manipulated and passed around, which is the way of sharing information from node to node to node. So if we have a workflow that goes from node to node to node, we may have a desire to have the result of the first agent or the first node, that context pass on to the next one in the workflow. And so that's done through this state object that's maintained throughout LangGraph. But each one of these frameworks does that a little differently. Like Autogen, as I said, has a team that's conversating. So they tend to have in the session, they tend to have like a memory that's maintained throughout the session that each agent has access to. So it's kind of like almost like a database or like an internal memory that every agent can kind of draw from in terms of the current conversation and any context that's been gathered throughout the conversation. So that's kind of how Autogen does it. Cray has something similar, except it instead of having that in memory, it can save it off to a cache, something like Redis, which is just essentially a data key value data store, where it can save the state. And again, the whole purpose of that is to maintain both of these really is to maintain memory and context. So. in order for each agent to have access to the conversation and kind of the chat history, um, as those agents are working together in this team or having this chat in AutoGen Career AI. And again, that's because if you have a multi-agent system, these agents are going to be working together. They're going to be passing information. Whatever the result of one agent is would be used in the next one typically, and they need to have access to that. And so you need some way of kind of sharing that memory or that context. And each one of these does that kind of in a slightly different way. So just pointing that out. They also get scaled and optimized in slightly different ways. They're just different Python packages. So they're managed slightly differently on that front. I don't want to spend too much time going into those because, again, they're more DevOps topics. Um, but relevant for us, I think, is the state management, which is important for agents, that sharing of information, right, from agent to agent to agent. I think that's relevant. And just to say, it's handled slightly differently from library to library. Okay. So that's something we may come across as we go. So all these things we may come across as we go through, examples today of them and get some exposure to them. Again, the goal for today, not to come away as experts in any one of these. It's more to just get some exposure to each one of these and see, how agent systems are truly built underneath the hood. So, in terms of security and compliance and observability, each one of these has different ways it can handle authentication and things like keys and role-based authentication. So each one can do that differently. Again, I don't want to get too far in the weeds on that part of it because it's more of the DevOps setup of each one. What is interesting is the observability. So what I have noticed myself from each one of these libraries is they have very good logging. Each one of them has good logging, so you can see in detail the various operations of each agent. So you can see every time it calls the LLM, has a conversation with another agent, every time it uses a tool, what the result of that tool usage is. And you can integrate that with other libraries like OpenTelemetry or different like log exporters or different logging tools like a Datadog or Elasticsearch or things like that to get really good observability into what your agent system is doing. But at a minimum, they all have really good built-in logging, which is important. So for agent systems, that's really, really critical. So you can see what they're actually doing when you're debugging them, right? So you can see what kind of LLM calls are they making? Are they making redundant calls way too often and driving up costs? Because that of course costs money whenever you're using tokens that way. Um, and also what kind of tool usage is it doing? Like, is it calling the right tools? Is it editing the right files? Is it accessing the right data that it needs to? All of that you can kind of see from the logging capability. Uh, so what I've seen is each one of these has really, really good built-in logging and they hook up to other kind of logging tooling that's out there, like a Datadog or Elasticsearch, those kind of things. And OpenTelemetry for kind of tracing instrumentation. So again, like setting all that up, not going to focus on the details of that because that's more DevOps stuff, but just to say they have really good built-in logging to see a lot of the details of the what's going on with the LLMs and the tool usage from the agent perspective. Okay. Okay, so that's just a little info about those frameworks. Again, one of our goals is to just go through each one of those and some demos and see some of those examples. Um, But so we may be wondering, why do those exist? And part of it is for efficiency. So if we have a lot of our agent systems built out in those frameworks, we have the ability to reuse them for automation. And that helps a lot of business needs, right? So we're building our agent systems for specific business impact. We don't need to start from scratch. If we have those components already built out in one of those frameworks, we can kind of reuse it. And that it also gives us a good starting point for managing our agent systems. We don't need to start from scratch and do bare bones Python code. When we use the frameworks, we get a lot of benefits. We get like built-in agent tooling, we get built-in logging and observability. So there's a lot of things we get out of the box with these that we don't have to do from scratch, which is nice, and it allows us to reuse these things. But uh, the question always comes up: which one of these frameworks should I use? And what I would say to that is it mostly comes down to preference, and also I'd say two things: preference and alignment of tasks. So depending on what you're trying to automate, it may make more sense to use something like a line graph if it's very, very sequential and ordered and you need things very sequenced, and it's very structured. I'd say line graph is a great choice. But if you want more open-ended conversations and deliberation and maybe task delegation, something like a Crew AI or AutoGen might be better aligned to that, and where it doesn't need to necessarily be in a predefined sequence and it can kind of go back and forth, then those might be better. So, which one to use sometimes does depend on the workflow itself. Other times you can get away with using any one of the three. Just comes down to preference, almost like which one to use, TensorFlow or PyTorch. Remember, that kind of comes down to preference. Might also come down to what have you done in-house before. If you to a company that has built a lot of stuff already in Crew AI, you're probably just going to stick with Crew AI, right? If they've already done a lot in LangGraph, probably just going to stick in LangGraph, unless there's a good need to switch those. So a lot of it comes down to, what examples do you already have? Because you can reuse them, right? You could stay in that framework and kind of reuse them. So going back to selecting the right one, in terms of LangGraph in particular, it's helpful for workflows that are very sequential, as I said. They may have dependencies from task to task that we need to have access to, like the result of task A, pass that on to task B, do that one, pass that on to task C, etc. It also does support repetition. So if you need to do looping, you can have a graph that has a looping edge, so you can kind of redo operations as you need. Um, and so here's some examples on this slide of some use cases, things like loan application processing, where you have a very structured workflow, right? You're going from a document verification to an eligibility check to a loop if things are missing, and then maybe an escalation if fraud is detected. All of that could be a graph, and we could build out that graph in a very structured way. So that's a good use case for that. Patient intake, again, that's one that goes from kind of point A to point B to point C. We collect symptoms, suggest tests, handle missing data, pass off to a human in the loop, doctor. Um, Flight disruption handling, so maybe like an automation workflow there for handling delayed flights, rebooking, rechecking preferences, sending notifications. Again, very structured workflow. And if we have a lot of structure to it, it's a good candidate to be put in this graph sort of structure in LangGraph. Okay, so just some examples. Of course, there's many more, but those are just some thoughts. And again, we'll hopefully do some demos today where we see some interesting examples too. Autogen, what is it useful for? Again, it's kind of the situation I talked about with collaboration and building a team where they can kind of debate, conversate, have multi-agent conversations. And this is really good for things like ideas, brainstorming, uh, code review, these kind of things that you want to build a consensus around or have some debate over. So maybe like a bug fixing, code review agent. workflow. So we need to propose a fix. We have a tester agent that can run test cases, an architect that can review design, and then they can kind of conversate and go back and forth and iterate on the solution. So something like a code review agent would be, a good use case for something like an origin. Strategy planning, that's another one. Again, you're going to debate. You're going to have multiple agents set up in your team. They're going to conversate. Um, they will refine their planning, and they'll do that all in kind of this group chat setting. Um, Complaint resolution for customer service, that's another one. So review the complaint, verify all the rules, legal can check compliance, and you have these different agents that can work together to try to figure out how to resolve the customer complaint. How about scheduling staff across multiple stores? Oh, this is a good question. So, how do we identify the case in which will benefit from AI versus old-fashioned automation framework? So that's a good question. I would say where you're going to benefit from AI is wherever you want to use the capabilities of the LLM to plan and think autonomously. So in other words, like you don't want to define all of the rules, you don't want to define all of the solution framework. You just want the agent to be able to think on its own and come up with a solution. Um, so in a situation like that, where again, you're not prescribing all the details, you want the LLM to think on its own, maybe given some context, so like some guardrail context, ultimately think on its own to come up with a solution. That may be a good case. Uh, that may be a good case of where you don't need to you may be better off using an LM and something where like you have very specific rules and you don't need an LM to think and plan out a solution. And you can just get away with using regular functions and it's very deterministic. Um, and you don't need any planning done, you don't need any thinking done, you don't need any um kind of planning and tool usage combined together. That's where old-fashioned automation probably comes into play. So again, the thing that AI brings to the table, generative AI, is the LLM like planning process, acting very autonomously. You're not really in the loop very much, right? You just provide the prompt and which is the task and let it go. Does that make sense? So that's what you're really gaining from the generative AI is the planning aspect and the thinking of what to do on its own rather than you providing the rules and the direct kind of do this, then this, then this, then this, and this, which is all codified in kind of rules. Yeah, example of planning process. Probably the best example I have is with like a coding agent, like a Claude Code or a Codex or something, where it can plan out what to write. So it can plan out like a design and then do an implementation of that design. So you can give it a very broad task, like build me an app to find the nearest restaurants within 5 miles of me and uh, aggregate them onto a screen with all the reviews and whatever, whatever features you want. It can write all the code to do that, but in order to write the code, it's going to have to plan all that out, right? So that's where you're really utilizing the LLM to like automate the coding process. It's thinking, but it has to plan that out. So it has to first think of what steps do I have to take? First, I need to build like these various functions, and then I have to fill them in, and then I have to write tests, and then I have to integrate them. Then I have to build a UI, right? It's going to plan out all those steps, and the LLM is going to do that autonomously, or the agent is. Um, so that's an example of the plan. Like it's thinking, what steps do I need to do to complete this task? And all you're doing is providing the general task, like build me this app. And it will think about all the steps it needs to take to complete that. You're not prescribing those steps, right? You're not in the loop on those steps. The LLM is planning it. Is a model trained to build that process? Yeah, the LLM is. Absolutely. The LLM is trained to do that. That's what the model, like the large language model has been trained to provide responses to those prompts, which are, build me an app. And part of that is planning out what that looks like. And yeah, the model has been trained to do that. But keep in mind, it's been trained against a lot of data. So it's one of those like transformer-based large language models, like a Claude, Sonnet or Opus, very large language model that's been trained against a lot of examples, a lot of code bases, like think of like all of GitHub, in order to be able to design code. So usually you can, use something off the shelf. You probably wouldn't need to retrain a model from scratch to do that. So I wanted to talk about Crew AI a little bit too. So we talked about AutoGen and LangGraph. Some examples for Crew AI might be doing like market intelligence. So we again have multiple agents in the mix in our crew. So kind of like AutoGen, we have a team. They chat amongst themselves. Crew AI, we have a crew, which is a team. And there's multiple agents in the crew. So we have a researcher agent that's responsible for gathering competitor data, an analyst agent that's looking at different trends, and a writer agent formatting the final report. And so they work together in the crew, but inside of that crew, there's kind of chat going on to delegate, to plan and delegate like who should accomplish what task. So there's an overall prompt that from a user saying, I want to do market intelligence or build a market intelligence report around this product, let's say. And then the crew has to figure out how to get that done. It's going to conversate. It's going to uh, plan out how to do that, and then basically delegate and figure out based on the various agents who's best at doing what task, and then going out and accomplishing those tasks. So again, we will see. This is the first place we're going to start with some of our demos. I want to start on Crew AI. We'll see some demos of this where we build out multiple agents. The example we're going to do is actually going to be the second one, this travel itinerary planning. So we'll have a destination expert that's responsible for identifying attractions to visit. We'll have a budget analyst to optimize costs and a scheduler to basically build out the itinerary. In a more advanced iteration, maybe it actually has the right tools to do the bookings itself. So maybe it integrates with, various APIs like on a travel website, and it could actually, do the booking itself. But the demo that we'll do will just be writing up the itinerary, not actually, doing the booking. But that could be a real use case is actually arranging the booking. One other use case could be like an incident response team. So again, this is a team or a crew. We have multiple agents here, a threat detector to locate anomalies, investigator to look at logs, and communicator prepares a summary. And these agents all work together in the crew, delegate, figure out who's best at what based on some of their background information about those agents that we're able to set up, that can dictate, okay, this agent's really good at anomaly detection. This agent over here is really good at looking into logs. And this agent over here is really good at just writing in general or writing summaries. And we would delegate out, the tasks to the appropriate agents. Plan and then delegate. So again, we'll see that. We'll see how to set up these agents. We'll see how to put them together in a team, and then basically execute them on a task. So we'll see that in some of our code. But just going back real quickly, you can see the differences. The lane graph is going to be better suited to things that have a lot of structure already. So we want things to go in a very specific order, and it's easily modeled as a graph. Those are the best ones for lane graph, and then kind of AutoGen and Career are better for team-oriented collaboration. That doesn't need to go in any one particular order, but we do have the ability to kind of delegate and debate when needed between those two. So you can kind of see the differences there. Okay. So that being said, wanted to talk about the some of the challenges and where LLM based agents are kind of going. And then, as I said, we'll take some time to start diving into demos with them. Um, but wanted to wrap up this lesson, which is more of an introductory lesson to agents, by talking about some of the challenges. So, the first place to start with these agents is they are very powerful, right? They can help automate things and help make our life easier. But they do have a lot of implementation hurdles and challenges that are um, very real. One of them is the um, basically the performance bottlenecks that we see with these agents, and a lot of that is tied into the LLMs themselves, right? Because LLMs take some time to generate responses and to do planning, and especially in they're working in a team to conversate and delegate. That all takes time. So, and it's not deterministic, right? So there can be a real performance bottleneck issue that even if you're using the latest and greatest and kind of fastest models, it's there's still going to be latency concerns generally whenever you're using these agents because they are going to take some time to come up with a solution, plan it out, and then act, and then maybe iterate on that. And there can be latency concerns, especially with really complex workflows. So that's something people are always thinking about with these agents is like the time it takes to return a response. And if you're doing something that's very time sensitive, like trying to identify fraud and flag it and escalate it, you want to be really wary of time, or you're doing something like stock trading or something. So these agents are very, sensitive to latency in some ways, but so that's always a concern. Even down to like a, day-to-day concern of just interacting with LLMs, we are probably aware that, generating a response can take time depending on the model. There's also, similar to that, there's scalability issues. So, um, it can be a challenge to manage these workflows, especially from a DevOps perspective and infrastructure perspective, especially if you want to use your own LLM and not have to rely on paying a provider for the LLM. That can be a real concern is how to scale out our workflows, how to scale out our LLMs so we can use them in many different situations with our agents. Um, and so a lot of organizations are facing those kind of challenges of getting up and running with like a self-hosted model, for instance, or fine-tuning that and using a self-hosted model that's fine-tuned, and then making sure it's the infrastructure is there to balance the load across maybe many different agents that are utilizing those LLMs. Um, so that can be a challenge. It's just the fact of just managing the LLM infrastructure to use it with agents. That may be interacting with them very frequently, and you may have lots of people using agents, lots of workflows, that can lead to real scale challenges, right? Um, the other concern is with any generative AI is bias in the training data. So that's not unique to agents. That's true with anything, especially with LLMs that are being trained to generate responses. And there's a concern that they could provide biased responses or biased or even false answers, and make mistakes because it is, generative. It's not perfect. It's not deterministic. It's not always the right answer. So there's concerns there of answers being biased or just flat out wrong, right? If they're coming from an LLM, especially when working with agents, right, that are using the LLM to kind of plan and do things. We don't want those to be biased for especially when you're using these agents in kind of these automated workflows like loan processing or scholarship processing or those kind of things. Don't want them to be biased. So there's definitely ethical concerns, and that's true across, again, not unique to agents, true across a lot of facets of AI, but certainly true here because LLMs are at the forefront of agent operation, right? They're a key part of agents. So, given those challenges, what do we see with the future? Well, we see agents evolving every day. It seems like they're getting better and better. In certain areas, like autonomy, for sure, like being able to do things without human in the loop really at all. Um, Being able to basically learn from their mistakes in real time with human feedback, and then being able to take that forward and apply that to future tasks. That's a huge thing we kind of see and expect over the course of the future. Um, we also expect more domain specific learning. So as agents are being deployed in different domains, they're able to learn from those domains, and they don't have to be explicitly fine-tuned. They can kind of learn from being exposed to data. It's what we expect to happen. They just get better and better at operating in those domains. The more they're being exposed to tasks and questions and data from those domains, they just get better at handling that. That's the hope, and they don't need to be fine-tuned. Um, and again, so kind of that's what we're getting at here with the human AI symbiosis point at the bottom is the more we use it on our data, the more we expose it to our tasks, our workflows, our data, the more it can kind of pick up on that without having to be explicitly retrained and fine-tuned. We can kind of integrate that into the architecture so that it learns from that context over the course of usage, um, and preserve learns to preserve that context essentially. That's what we expect to see. We also like as hardware gets better and the models get better, we expect there to be more efficiency gains. So so the latency becomes less of a concern. And we've seen some progress on that. Like the models are getting faster at returning responses, and we've seen that over the years. Continue to expect that to be true um, over time. And there's thought that we're kind of hitting a plateau on the intelligence of the models. Like the models themselves aren't going to get that much exponentially better, but the infrastructure of serving the results and the actual processing of information gets faster, so you can return answers faster. Okay, so just to recap all of that lesson, we're talking about these LLM based agents that what makes them unique is their ability to operate without human intervention, especially two main things, right? Is using an LLM to think and plan, and then having access to tools to take action on its own. And we say plan and think, that involves what tools is it going to use, what steps is it going to take to complete a task, those kind of things. That's all driven by the LLM. And so there's a lot of business use cases for agents. Um, and what we're going to see is there's, some of those use cases can be modeled very effectively in these libraries like LangGraph, AutoGen, CrewAI, to build out these agent systems to accomplish those use cases. All that said, there are challenges we talked about: bias, security, scalability. And so not, part of that can be tackled through logging and observability. So kind of monitoring what the agent's doing, how it's processed, how it's making LLM calls, what kind of tools it's using, and then understanding that. So maybe we can make it more efficient and optimize it, make less redundant LLM calls, those kind of things. Um, but in the future, we expect the models to get faster. We expect them to improve and learn better. And we expect generally for them to be less biased and more correct. as they're being tuned and updated with new data all the time. We expect them to get better at reasoning. So I want to talk about Crew AI and give an introduction to that library to help us build examples of agent systems and agentic workflows. Um, so what I'm hoping to get out of this is basically explore Crew AI, especially the main components of it, so we get some familiarity with how we build agents, how we put them together in the crew, how we give them tasks, how we give them tools that they can use, and then see how they interact together in the crew to accomplish those tasks. Um, and then we'll do that over the course of some demos throughout. And the main application that we have in mind for this demo is a trip planner itinerary agent. So we will, again, be doing that through multiple agents in this system to help us plan out a trip. So we'll see that over the course of some demos. So going back to just some background information about Crew AI as a package, again, it is a library that helps us build and manage a team of agents, so a multi-agent system. And each agent that we build as part of the crew, so the team of agents is known as the crew, hence the name Crew AI. Each agent will have access to various tools that we supply to the agent, and they'll also have metadata that guides them on what their specialty is and kind of what their goal is and what their tasks are. Um, and that's helpful to know because um, each agent that we define as being part of the team has the opportunity to be unique. It has the opportunity to be specialized. It can use its own specialty LLM, for instance, that has been fine-tuned. And so each agent can be highly customized um, in terms of its specialty and what it's designed to do. And so that'll turn out to be a big deal is providing that metadata for the agent when we initialize it as part of the crew is kind of what is it good at? What is the agent meant to be doing? What is it supposed to be focusing on? And what is its role in the team? So kind of like no different than a team of humans. What is everyone's role? And so we'll define that as part of the crew. Okay. So we'll see that in the demos. But that's the main idea is Crew AI is oriented around the idea of building the crew, which is just made up of a team of agents. Those agents have tool access, they have LLM access, they have roles, and they have metadata about that kind of orients them to what they're supposed to be focusing on. And again, it's a lot of it's going to come down to what is the syntax of putting that all together, right? What does the Python code look like that puts all that together? And that's kind of what we want to see. So, as an example, we could imagine putting together a crew that is building an app. So we have maybe a researcher agent who's doing some background on what the best packages are for that or what the design should be. We may have a code writer agent who's writing out the code, and then we have an engineer who may be testing it, architecting it, those kind of things. But basically, our way we would approach building a system for this is instantiating multiple agents. So these would be our agents here, and then putting those agents together in a crew. So we have one agent, we have a second agent, and then we have a third agent. We put these agents together inside of a crew, and then let the crew kind of operate on this prompt. So there's a user prompt that's kind of launching the crew. And then the crew will delegate and plan out and figure out what's the best way to approach accomplishing that, given that we have access to these three agents, which have various tools, LLMs. And as I said earlier, like each one of these agents could have different tools. In fact, most of the time they will. Like the writer may have tools to edit code files. The researcher may have like internet or Wikipedia search API tools. The engineer may have like execution tools to execute code and debug it. Um, so each one can have different tools, and each agent can also have different LLMs that they can use. So as I said, it gives us the ability to specialize each one. Like this one may specialize in code writing. This one specializes in research. It can use a completely different LLM that's been fine-tuned to do that task. Um, and so the other thing about these frameworks and what's really nice about them is when we build an agent for this crew, there's no reason we can't copy and paste that code and use it in a completely different crew. So maybe we have a different workflow we're trying to automate, and that would require building a different crew, but we can kind of copy and paste this and use this in some other crew. And we can use the engineer maybe in some other crew, right? And so uh, that's one of the nice benefits of this framework is if we build out another Crew AI app or a Crew AI frame workflow, there's no reason we can't reuse some of the agents we've initialized in other crews. We could mostly reuse that, which is nice from a code perspective. Can one agent use multiple LLMs? Yes, it could. And can it use other models? In theory, it could. It could use a model as a tool. So, we maybe we have a need to make some type of prediction, and run some sort of inference. In which case, maybe we are hosting our model on some endpoint, and we process some data and pass that through the model as a tool. That's possible. And it is possible for an agent to use multiple LLMs. It's not very common, I would say. Usually it will choose either the user will choose one of them. Like the agent could have access to multiple, but only use one of them when it's actually being used. It's rare that it would need to utilize multiple LLMs. Rare, but in theory possible. But yeah, it could use other models, which would be like having a prediction tool. And so you can imagine building out like a fraud detection workflow, in which case you have one agent like gathering like maybe parsing transaction data, gathering it, and then passing that to or using a tool which is sending that data along to the model, generating a prediction, and then the agent interprets that prediction in some way and does something with that, right? Maybe escalates it um or sends an email or a Slack alert or something, right? So that totally could be possible where using a model is equivalent to using a tool, if that makes sense. Very, very possible. In fact, in the demo that we do, I'm going to show you how to build a custom tool. So it could be that part of the custom tool is running a model on some data. That's totally possible. Like a deep learning or a machine learning model or something like that. Great question. So in production, how do you host the agents and access LMs? What is the cost model? Um, so I'll give you what's typical. So what's typical is your agent system is typically what we would call containerized. So you write your Python code, but you execute it inside of a container, which is like something like Docker. And that container, which is a kind of an isolated compute environment for that agent system, is hosted in some deployment environment that you have, usually something like a Kubernetes, which manages containers and orchestrates containers. That's a very typical setup. So you write all your Python code, it gets built into a Docker container. That Docker container gets hosted somewhere in your cloud infrastructure like AWS or Azure, Kubernetes. Um, and you're so usually you're paying for the infrastructure, so you're paying for the compute cost of hosting that container. Um, and then you are typically interacting with the LLM through an API. So your agent is calling the model, and you usually have an API key you're setting up as part of that agent. Actually, we'll see this in the demo, is like the LLM we set up as part of the agent is just really interacting with the LLM over an API call. And so you're paying for the token usage there of your API calls. And so that's, some fixed cost per token that you're paying that provider. But your agent is very similar to any other software that you're running that's being hosted on your own infrastructure. So you're paying for your infrastructure, like your compute, your container compute resource. Um, so you're paying a rate for that, and then you're paying for the token usage. You're usually paying for those two things. And so what I want to say is we will see examples of that LLM interactions. We'll see an example of setting that up as part of our agent setup. But we won't be going into like the deployment aspect of this stuff because that's a little beyond the scope of this. That's more for like a engineering DevOps kind of setup. Did that answer any of that? Or did you have further questions on that, or did that help answer a little bit? So yeah, you host them on your infrastructure, usually like a Kubernetes cluster that you have managed in your cloud, like your Google, GCP, or Azure, or AWS. And you're hosting your agent code, which is going to be basically like a Python system, like you would any other software, basically exactly the same way. Okay. Okay, so excellent question. I wanted to move into a little bit more on Crew AI, in particular the core elements of it that we would use to build a multi-agent system. Um, and so the four things that we need to talk about in order to build that up are going to be agents, tools, tasks, and process. So just at a high level, the agents are going to be objects from the framework that we will obviously utilize to do things. So we will be able to build agents relatively easily from Crew AI. And then the tools are what the agents use to do things, right? To take action. So these are things like calling an API, like doing an internet search, executing a custom function, maybe even calling a model, like you just suggested. Those would all be examples of tools. And again, in the demo, what we're going to see is we have a way to build a custom tool that the agent can utilize. So we'll have a way to build agents from Creo. We'll have a way to build tools and assign those tools to agents so that they have access to them. Because every agent, in order to be effective, really needs tools, right, to take actions. Um, then these last two, so the tasks are essentially like they are steps that we want the agent to or the agents to take or kind of like miniature goals to keep them on target and kind of give the agent something to focus on so that they know how to delegate. So tasks are important to assign to agents so that the delegation can kind of map the overall prompt into, okay, we're going to break the overall prompt down into smaller tasks. And this agent, it has been designed to accomplish these kind of tasks. So this is a good agent for this step. This agent over here is a good agent for this step because it aligns pretty well with that task. Um, so we will practice defining tasks, which help orient the agents on what kind of work delegation they should be focusing on. And then process is just the way we will orchestrate the agent. So whether that's in sequence or whether that's in kind of like a manager worker setup, or maybe in like a debate setup in a similar way to AutoGen and like the group chat concept. Process just defines how we orchestrate the crew, how we manage the crew, how does it get managed? We're going to go through and have some examples of each one of these core components of Career AI. So agents, tools, tasks, and process. And we're going to build out some demos to show off each one of these things that are going to be critical to, putting together a full agentic system. So that'll be kind of our focus is breaking each one of these down into some examples, really. So the first place I want to start is with tools because it makes sense to define tools first, and then of course have those tools be utilized by agents. So the first place we're going to start is with tools, as I said, and tools are what give agents their ability to take actions, right? So these could be like web search tools, data analysis tools, code execution tools. File writing tools, many tools that are out there. The two primary sources of tools that we are interested in when we build an agent are LangChain. So this is a library that is a very special library that helps us build LLM applications, but also helps us build custom tools for agents to use. And I'm going to show you how we do that in code shortly. So we can build LangChain based tools very easily. Crue also has a number of tools built into the library that you can pull off the shelf, kind of like how in, Keras from TensorFlow, we were able to pull in models off the shelf. Um, Same idea with Crue. We can pull in a bunch of tools off the shelf as well that are already pre-built that we can assign to agents. Um, the thing that I want to show us in the demo is how do we build a custom tool to do something we want to do. And a very good example you mentioned earlier is something like maybe run a prediction through a model. That could be a custom tool. I want to show you how LangChain helps facilitate building custom tools, which could be, we could think of them as just basically functions, right? Tools are just the way for the agents to do things like edit a file, do a web search, do a database query, um, integrate with Slack, integrate with Google Sheets, integrate with Salesforce, whatever it is. Um, so one of our ideas will be to examine how we can build a custom tool and then make that tool available for the agent to use when we define our agents. Um, but as we said earlier, tools are a hot topic because there's a lot of integrations out there that can be difficult to work with. And so we're not going to get into it here, but one of the things that makes connecting agents to tools very possible is something called MCP. We kind of highlighted this, um, you know, last week, but we won't need that here because the tools that we will build will be entirely self-contained to the library, and entirely used within the Crew AI ecosystem. So, MCP would be more relevant for something that exists outside of that ecosystem that we may want to use, like maybe like a Salesforce integration or something that Crew AI would not already have. and in which case we need a way to communicate with those tools and use them, which would be more of the realm of MCP. But these are going to be tools that are entirely, Python based, entirely built with or in the Crew AI ecosystem that we can use with our agents. Okay. Okay. So some of the key features of tools that we are really looking for is versatility. So basically, we want the ability to have pretty common tools that any agent would want to use. So things like the web search we talked about, um, maybe data analysis, maybe code writing or file editing. Um, so we want a good range of tools, and luckily that's doable, whether that's from the toolkit that Create AI already provides, or we can go out and write our own very simply using LangChain. So I'll show us how to do that. So we want versatility, and again, we get that not only versatility but customization, which we get from being able to build our own tools. Integration, so we want agents to be able to utilize these tools without any issues. And so again, everything that we will look at will be entirely within the Crew AI library and package. Um, and so that really won't be an issue. If we had to use tools that were, again, outside of that, that were integrating with some custom software, like uh, a very specialized tool, that's where we may need something like to integrate that, we may need something like an MCP. But we won't need that here in the examples we're going to do. Customization. So we want the ability to create new tools whenever we need them. And so we will have that ability fairly easily, again, using a library like LangChain, and Creo is very compatible with LangChain tools. So that's very nice. LangChain provides a really nice template for building a tool, and then Creo AI kind of understands that template so it can work with those LangChain built tools really easily. Um, we also want built-in error handling. So, like we want nice logging, we want nice exception handling where necessary. So, luckily, the tools again that are from off the shelf from Crew AI are built with those in mind. So they have very nice logging and kind of error handling built in. But if we built our own, that's something we may consider adding. Um, is how to handle any tool usage errors and what to do as kind of a fallback or a default. But the built-in tools off the shelf generally all have that, so that's very nice. It's very easy to use. And also working with tools inside of Creo AI, we try to minimize redundant operations as much as possible so we get efficiency. That just means that as we're using tools and we generate context from that, like we get a result from that, we have the ability to Creo AI can internally cache that so that we don't need to redo that operation if we're trying to grab that context. We can kind of just grab it from memory. We don't need to go back and do another tool usage just to grab that result. Um, so that's possible. And that goes back to that shared like state management we talked about earlier. Okay. So that brings us to a demo that I want to take us through on building tools. So I will share that document with you in the chat, and then I will show you some of the code to build a couple tools. The tools that we're going to build are going to be used as part of our overall agent system that we're going to work up to in Crew AI. The tools that we're going to build are going to be an internet search tool, mainly for the travel researcher to be able to go out and fetch information about different destinations that we could travel to. And then a calculator tool, which would be useful for doing like budget calculations. Um, So we'll have both of these tools available to our agents, um, if they need to use them. So I want to show us how to build those custom tools using LangChain. So let me go over to that and then share that demo with you. So again, these are some demos that are included in our AGS course. Let me go and find that one. And then okay, I got it. Let me share it with you. Okay, so I uploaded that and then let me share my screen. Okay. So hopefully you guys have this now that I just uploaded it. Obviously you wouldn't have had this before because again, it's not part of our regular materials, but just providing it here as again, it's part of our AGS course or AGS program on advanced generative AI specialization. Um, but just walking through this here, our goal in this demo is to see in the code how we can build some custom tools that our agents will use. So that's the idea, right? Take a look at how we can build custom tools for agents to use. And so what we're going to do is I'm going to show you how to set up the example project in VS Code. This demo uses VS Code. It does not use Colab, although you could get away with doing a lot of this in Colab. That wouldn't be an issue. But it assumes you're going to write .py files and rather than do everything in notebooks. So I'll show you that setup when we get into the demo. But essentially, we're going to create two files, a calculator tools.py file and a search tools.py file. And we're going to put some code in there. So we're going to have those two files and we're going to put some code in there that I'll show you to end up making the custom tools. Um, the thing that we're going to do, it's going to look like this. And again, I'll show you the code for it in a moment. But the thing that we're going to take a look at that helps all of this work is really this LangChain tool decorator here. So this thing is immensely helpful for building a custom tool. We haven't seen it yet in our Python code, but this at tool is what's called a decorator. Um, in Python, what's called a decorator, which is kind of like a special way of inheriting the features of that decorator. Essentially, what this does is it makes this function behave like a standard tool template. You think of the tool as kind of like the at tool as providing a template, um, as kind of providing a template, and this decorator is kind of dictating that this function should look and behave like a LangChain tool. Um, oh, can I share it? Were you able to get it? It should be right above your. I can share it again. It was right above your message. I'll share it one more time. I just posted it again, so hopefully you have it now. No problem. Okay. So as I said, this I'm gonna open up this code in VS Code in a moment and share the code file with you so you have it. Um, but essentially, the demo wants you to write out this file, this calculator tools file. The main feature of it is this tool decorator. Because this is like any other Python function, essentially. But when you have this at tool, it makes this function behave like a tool from LangChain. It makes it act and behave as if it was a tool from LangChain. And why that's so helpful is because crew AI agents know how to work with these tools very well. They know how to work with it seamlessly. And so when you instantiate an agent and you work with the agents that, which is what we're going to do in later demos, they will be able to work with these tools very, very easily because this thing has kind of a standard template to it. It's this tool decorator. It makes this function behave very much like any other LangChain tool, which is kind of like a standard interface. Um, and that's how the Crew AI agents know how to work with those tools. Okay, so I'm going to share the code with you that's in this. In a moment, but that's one tool we're going to build. The second one is inside of a search tools.py, and this is one that is going to do a web search by sending a URL API request essentially. And so the basics of the code kind of looks like this. And what you can see is, again, the thing that's formatting this tool to be in a standard template so that our crew AI agents can work with it is this tool decorator. So there it is again. It goes right. Decorators in general are prefaced with an at. You know the at symbol, and they go right above a function. Right above a function. And what that does is it means this function follows this interface or it follows this format or this template. And so this is a internet search tool, and this is our logic of what that tool's doing. And so, the question was asked earlier, could we use a model? Yeah, all we'd have to do is come in here and write some code that has a decorator with the at tool, and then has a custom function to process a model, right? So process some data through a model and generate a prediction, like a probability or a class, of whatever that prediction is. Like if it's going through a neural net, what is the class of that prediction? Or regression, like what is the value? But like this function could do anything. In this case, it's doing an internet search, which is just calling this Google URL, sending our query through in a request, API request, um, and returning the top four results and parsing those top four results. So the rest of the code, it's kind of cut off here, but again, I'll share the file is posting. So this is an API post request to that URL with our data query. And we are parsing the results here to take a snippet of the returned result from the top four web pages that are returned. And that's going to be our research tool. Essentially, do a web search, return some data from that. Um, and join that together in a string. So all that gets put back together. All those top four results get joined together in this string. Okay, but the magic of it again is more or less it's a function, but decorated by this tool, which makes it special. That's what makes it behave like a standard tool. And this at tool comes from LangChain. So this decorator comes from LangChain. You can see here we're importing it from langchain.tools. We're importing the tool decorator, which is used to make these functions look like a standard tool that CrewAI knows how to work with, knows what to do with. Okay. So let me pop over to, so that being said, let me pop over to VS Code and share the code file with you for the demo. And then kind of walk you through the project setup if you're interested in following the setup. Um, so let me do that. So let me go over to VS Code and share with you the files. All right. Can you guys see my screen okay? I'm over in VS Code now. Um, Yeah, you can use Colab. There's no reason you can't use Colab. You can basically put this code in a cell in Colab and it would do the same thing. So certainly, yeah, you can feel free to use Colab. I'm just going to use VS Code and show you how you can set some of this up if you want to um, using VS Code. But absolutely, you can use Colab. If you're using Colab, just put this in its own cell. So the code that you see in a .py file could go in its own cell. That's the only thing. All right. Okay, so a couple of things about this demo that I want to make you aware of is, first of all, the project structure. So what I did is I started a new directory, a new folder, and you can call that folder whatever you want. I called it this MSAI demos. You can call it whatever you want. So I have a folder here that I created, um, and initially that folder was blank. But what I did is inside of a terminal inside that folder, I used a tool that I want to share with you all, which we haven't used before, called UV. So it's a CLI tool, which is used for managing Python projects and installing dependencies in particular. So it's called UV. And so there's a few ways to install UV on your system. You can, if you have Python installed already, you can actually just pip install UV. And that will install UV so you can use it to manage your projects. The other way to do it is to go to this link and follow the instructions to install. So they have Windows and Mac OS instructions. So again, it's a terminal and CLI tool to manage Python projects. So you can follow that link there. And by the way, this is what essentially everybody in the industry uses to manage projects. It's super popular. And I've used UV for a couple years now, and it's fantastic for managing projects. And nearly everyone I know uses it. So I think it's a good tool to be aware of. Again, it's just for managing projects, managing dependencies, virtual environments, especially for like your local machine. No, if you're using Colab, you don't need UV. If you're using Colab, you will need to install some packages into the Colab environment. Like, for instance, you want to install LangChain. So you would want to run the typical like pip install LangChain inside of a cell to get that to run. So something like that, and I can paste that in the chat. You'll want to run something like that in order to install. But if you're running locally, that's where you want to use UV. You want to use something like UV to manage your dependencies. Um, and it's also really fast. So it installs packages really fast. It resolves dependencies really fast. Manages your virtual environment really fast. So it's a really amazing tool to kind of um, do everything with your Python project. So highly recommend exploring it and maybe trying to get it to be used for these demos if you can locally. If not, Collab works fine. You just have to install, you have to run your pip installs inside your cells, install the dependencies for this. Um, so once you have UV installed one way or the other, hopefully you're able to get installed. You can pip install it. You can follow the instructions on that I pasted earlier. You'll know it's working if you can run the UV command. So if you can just inside of your terminal, um, you can run UV and you see all of this kind of menu of options, you know that it's working. Um, so you want to get to that point where you can tell that it's working. And the reason that is because basically you want to open up your terminal within VS Code. You want to have that blank folder available, and um, you want to initialize the project by running the command uv init, and that will kind of initialize the project inside of that folder, and it will populate a bunch of these files for you. Um, So I'll paste that command. So in a blank folder, if you run the UV init, it will initialize the project for you and give you a few of these files. It'll give you a main.py, it'll give you a PyProject toml, it'll give you a README, it'll give you a Python version file where you can change which Python version you want to use. So if you want to use an older one, like 3.11, 3.12, 3.10, you can change that in here. And then your virtual environment would use that older version. This is the latest, so I'm using the latest. Um, but you have flexibility to change that. It now when you first initialize a project, it gives you a main.py that's very blank and basically just gives you a print statement. Um, and so let me make a new file just to demo that. So what it should do is give you a main file that basically has some code like print, hello world, something along those lines. Print with maybe the name of your project and maybe a little bit more code, but it gives you some basic Python code like this. And the reason it does that is so you can test and make sure everything's working by doing UV run and then your code. So something like main.py, or in my case, I already have a main.py, so fake main.py, which would print out which will just execute the code that's in that Python file. So, no, so yeah, maybe I'm going a little fast. If you're in Colab, you don't need to use anything with UV. This is just for the folks that are running locally on their own machine. I recommend using UV. And I'm showing it to you on purpose because I think it's a good industry tool to be aware of in the Python world. But no, if you're in Colab, you're not going to do anything UV. Nothing you need to do is UV. You're just going to use pip to install some packages, and you're going to write all your code in cells. So Colab, nothing UV. UV is only for local Python. Um, yeah, it should be. So you want to, in your main, when you run UV init, Um, so you should be navigating to a folder. Um, Actually, I can show you I can just do a new folder. I'll just do a blank folder and show you what that looks like. So I'll do um, new demos. I'll share the code in a second. I don't have a notebook for this because this demo wasn't done in a notebook. It was meant to be done in VS Code locally, but you can paste the code into the notebook. I'll share the code in a second. I'm mainly just wanting to show you how you can set up a project in general. I just want to show that off quickly because I think it's useful to know. I think it's useful to know. So what I'm going to do is open up a new blank folder. So there's nothing in this folder. So this folder is completely blank, right? It has nothing in it. What I'm going to do is launch a new terminal, and I'm going to run the one. So assuming you're local, so this is not for any of the Colab users, just for local. You can run UV init, which will initialize a project, and you can see right away it gave me a bunch of files on the left, right? It gave me a bunch of files on the left. And it gave me this main file in particular with some basic print code. And the way I can test this is all working is if I can run uv run main.py. What that's going to do is create a virtual environment for me, and it's going to execute this file. So we can see it created the virtual environment. It is using this Python version because that's what's in here. And it executed this Python code to run that, right? UV run main.py. So if you're local, only for local, highly recommend using UV to manage your project and install packages. Um, and I'll show you how to do that in a second for the tools demo we just walked through. Okay. So for the tools themselves, the code, let me share that in the let me share that here. Um, so the tools themselves, what you're going to want is the uh let me find it. Why do you need to? Mainly, you don't need to. It's just part of this demo wasn't designed to use um, a notebook primarily because so I'll give you the main reason. One of them is when you're working with agents, generally you build a UI to work with agents, and UIs don't display very well in a notebook. So the UI component that we're going to build for this demo and with CrewAI is not going to it's not going to render very effectively using a notebook. So generally, when you're building like an agent system and you have a UI for it, it's going to be in Python code that's going to be outside of a notebook. So I know we haven't done it for other projects, but specifically for interfacing with agents, it's very common to have most of your code in PY files and then have some of that PY code be a UI. And notebooks don't interact with UIs very well at all in Python. It's just one of those things. It's hard to like launch and manage UIs from a notebook. So, and that's just because we need like that mainly because we need some code to have some way to interface with the agent. No, you can still, so it doesn't mean you're totally out of luck. You can still build them in Colab. You can certainly still build them in Colab. The thing that you're just not going to be able to do is build the UI to interact. You'll have to interact with them just through submitting a prompt in the code itself, like hard coded into the code. You won't be able to unfortunately build a UI to interface with it, but you can do everything else. You can build the agents, you can build the agent system. So when you're submitting a prompt to the agent, you just will have to hard code that prompt into the cell. You won't be able to launch a UI and like type in the prompt, if that makes sense. That's the only thing you'll be limited on. Everything else, like building the agents, you'll still be able to do in Colab. Okay. So give me a moment. I will share the code for you that is in those tools. Um, so I'll share the code with you that's in those tools. So here is the calculator tools Python file and the search tools Python file. And I'm actually going to just open this back up to the folder that I had that had those tools. So those two files are here. So I have the code inside of that calculator tool. So again, if you are working in Colab, you basically just want to copy and paste this code into a cell. That's all you need to do is just copy and paste this into a cell, and then you can execute that cell. In order to run that cell, you're going to need to install LangChain. So you're going to need to run, if you're in Colab, you're going to need to pip install LangChain in order to get this to work. That's in Colab. If you're in UV, in locally, the code that you're going to need to run to install anything is UV add. So UV add is the equivalent of kind of pip install. It adds packages to your virtual environment, and the package we want to do here is LangChain. So UV add LangChain. Now I already have it installed, so it's not going to show anything. But if you yeah, Colab already has LangChain, so perfect. You won't need to. So this code should work fine, where you copy and paste this into a cell and build this tool, this calculator tool. Again, if you're working locally and you want to install the LangChain package into the virtual environment, it's going to be UV add LangChain. And one thing you should see is when you add packages, they will automatically show up in this PyProject TOML. So it already shows up here. These guys aren't going to show up yet because we haven't added them. They'll be later in the demos. But at this point, you should see LangChain. That should show up here in this dependencies list automatically when you run UV add. The other thing you should see is it should install really fast. It should be lightning fast to install. It's really amazing. UV, that's one of its known amazing qualities about it is that it installs things really quickly. It's able to resolve all your dependencies really fast, figure out which version is compatible with what else you have, and install it really fast. Okay. So UV add LangChain. If you're in Colab, it's pip install LangChain, but it sounds like it's already there, so you may not even need to run it. And so you're going to want these two files, or these two, in Colab, it'd be two cells. Copy and paste this code into another cell. But see how this tool, this is the code for this search tool. What it's doing is, again, decorating with the tool, which is making it look like a LangChain tool, which is what is going to be um, helpful to Crew AI. It's going to use that in one of our later demos with the agents. It's going to use this tool, um, this tool object. Um, and this is just going to send a request to this API, and then kind of parse the results and bring them all together in this string, as what we get out of this tool. And then the calculator is doing something really simple. It's taking a string operation and running the eval, which will kind of parse the string and execute the math. So if somebody puts in a string like 150 plus 25, it's going to read that in as integers and then run the math. So that's what this eval function does. So it's a simple tool. Obviously, we can have very complex tools that do a lot of custom logic here in this function, but this is a very simple tool, which even has some error handling, right? So we're going to try to do this. If we can't parse this operation, we will return a syntax error. We'll catch that and return a syntax error string to say, oh, we tried, we had some invalid syntax. So our tool won't actually be able to be used in that situation. So you have those two tools. By the way, if you're running locally, I would recommend putting those two Python files in a folder called tools that's inside of your project. So inside of our project folder, you can make a new folder called tools, and you want to put those two files underneath of that tools directory. So see how I have my overall folder is MSAI demos, and then I have a tools folder underneath of that with these two files. That's how I would organize it. If you're in Colab, it's just going to be in different cells. That's fine. By the way, let me pause there. Anybody running locally, any luck with UV? Were you able to get it installed? Were you able to add LangChain to your project? Any luck with that? Okay, yeah, pip can work. If you already have yeah, so if you already have an environment, you can just pip install it into that environment. That works too. That works too. And it's exactly what you would do in Colab is pip install. So that works totally fine. The benefit of something like UV is to kind of isolate things, right? So you have your environment completely isolated to this folder. It manages the virtual environment for you, manages adding packages to you, and adding packages to the project. I mean, um, you may need to add, so if you get a command not found exception, you may need to add UV to your path. So I would do a quick Google search on, especially if you're on Windows, you may need to add UV to your path. So maybe you want to search that up. I'm not too familiar. I'm on a Mac, so yeah, I'm not too familiar with Windows, but I think that's a common issue. Okay, cool. So these are our tools. So again, just to recap the tools, which is the main, I know we got a little uh, side benefit of looking at UV, which I think is, helpful to see at least once because it's a really popular package manager. And if you, get into working with Python, you're probably going to come across UV at some point. But this is what, makes the tools is this at tool, right? It makes it behave like a LangChain tool. And so this function now behaves like a LangChain tool. Can I execute the code? So if I execute this, nothing's going to happen. In terms of UV, so the initial project has a main pie that should have something like this. What it actually had was the actual code was more like this, which was a print function, and then down below, it had something like this. And so if I run UV run, I can execute my fake main.py and it just runs that print. So there's nothing to really execute so far other than just executing like inside of Colab. If you run those cells with this code, it'll just save this function for later in our later demos. So yeah, there's no execution that we're running right now specifically, but you can feel free to run these cells, which will create these classes, right? It'll create this class and create this tool class. In Colab, if you run those, it'll just create this class. But it's not really like right now we're not doing anything with them yet. Just showing you how to build the tools. Yeah, no worries, no worries. Okay, very cool. So again, the point of this is to show off how easy it is to build custom tools, which comes all for free, really from this tool. Then we can just make a function that does whatever we want it to do, and it's compatible with Crew AI. So really easy to do that, and we can put our custom logic inside of this function, whatever that is. So here, we have an internet search, we have a calculator, and that's really just all of this logic. Inside of this tool. As long as we decorate it with this tool, that makes it behave nicely and makes it a familiar interface for Crew AI, which is nice. Okay. Any other questions on this tool demo so far? We still have a few things to do, right? So what we're going to do is put together next, I believe, our agents that actually will use these tools. So that'll be coming up shortly. We will build agents that actually use these tools in our code. So we have to figure out how to do that. But right now, we have a couple of custom tools that those agents could use in theory. Okay, very good. We created it. So this is our tool is all of this function. This is all of our own code. So we did all of this. The only thing we're using LangChain for is this tool decorator, which is like the interface, right? So this is the interface to call this function when needed. So um, essentially, this is the interface that Crew AI understands is if we make this function act like a tool. That's all that this it's almost like an inheritance of a class, right? It makes this function behave like a LangChain tool, but really this function is our custom logic. So we created the tool, which is all of this custom code. So this code could be whatever we want it to be. Like the example you gave earlier is call a model or make a prediction. That could be inside this function. This can be whatever we want it to be. But the point is it behaves like a LangChain tool, which is important from a function interface perspective of Crew AI. It needs to act like a LangChain tool for it to be usable from Crew AI. And so that decorator really does that. But this function is all of our own custom logic. No, no problem at all. It's a good question. Fantastic. Okay. Okay. So we have that. We have those two tools. And we're gonna, as I said, so where we're going next is to build a couple agents that will use these tools and then ultimately put those agents together with our um, crew to have our multi-agent system for doing an itinerary planning and travel, agent system. So that's what we're building up to, and so our agent will have access to these two tools, and we'll see how we can make them utilize those tools, um, as we uh, continue building out the rest of the demo. Thank you. So yeah, we can continue here. So I'm going back to the notes. We saw the first example of building a tool. I want to go to now building out the agents as part of the crew, which is kind of the main component of it all. That makes everything work, of course, is the agents. Um, so inside of Crew AI, this is going to be our main building block for kind of an object that represents an agent in the code. So, and this is what we're really interested in because this is the thing that interacts with the LLM. It utilizes tools to try to accomplish tasks, right? And so, for example, you could have a customer support agent focusing on resolving issues, a sales agent generating leads, securing deals, on and on and on. Every agent can have a unique role, and that's actually going to be crucial in setting up the agent as far as an object goes. So typically, when you're using Crew AI, that these are the building blocks. You may define custom tools like we just did, but then we have to define agents which will utilize those tools, but also utilize LLMs to complete tasks, right? So they're obviously a huge building block of building out the system. And so we need to learn how to build agents and then see some examples of that inside of the Crew AI library. So, in order to build out our team or our crew of agents, we generally want to know what our end goal is. So what is the overall task that the agent should be accomplishing, and typically what kind of tools will they need to get that done. So every agent that we define will have these kind of core elements. They'll have tools at their disposal. They'll have an LLM they can interact with, but they'll generally also have kind of task guidance of what should this agent focus on, or what is it good at, what should be its goal. And so for each agent that we put inside of our crew, we generally want those elements, and we're going to see how to initialize those as far as the code goes. But when we build our team, we should have an overall kind of goal in mind of what the workflow is. What are we trying to generally accomplish with this agent system? What kind of queries is it typically going to be answering? And then that can help us define which agents do we need to do that. And it may be that we might only need one agent to do that. Maybe we need a broader team of agents because there's going to be lots of smaller tasks that these agents handle. That might all be different from system to system. It just depends on how we decide to break those down. So, and then when we build our team and our team has those agents, we then have the ability to set up how they will execute. So I know it says here appoint a leader, and that is possible. So within Korea, you can set up a kind of manager worker setup, and we're going to explore that in the processes section. But um, you don't technically have to. You can have all the agents kind of collaborate together without a single manager worker setup. But it is very common to basically set up and appoint one of the agents that we build as kind of the manager. And then that one will be responsible for doing a lot of the planning and then delegation to the other agents as workers. That's uh, um, still, that could be optional to set that up, but it's something you could do, and I'll show you how that kind of looks inside of the code to appoint a leader. We don't necessarily need to, but we could, and I'll show us how. But what's bigger than necessarily a manager agent is having roles. So each agent that we build will have a specialized role, which will align it to particular tasks. Whenever we're delegating work, agents will have roles that will align them to those subtasks so that they can tackle those, and they can kind of act as specialists to accomplish those. And it could be, as I said before, we could have a very customized agent that has access to very specialized tools and a special LLM. We have the freedom to set all of that up, and we'll see that as we start building our agents. So we'll define a role. That'll be a really big part of defining the agent, along with the tools and the LLM. The role will be really critical too. So when we define an agent in Creo, these are all the things that we should be filling out for that agent, and we're going to see that in our code. These are all parameters of the agent object that we should be filling out in our code. Um, so they kind of align to what I just talked about. We have a role, which is a big one, that basically specifies the expertise of this agent with as part of the team. So what should this agent focus on? What is its primary role? What is its expertise? It doesn't have to be, it's a string, but it doesn't have to be a very long string. It could be a short and succinct string, almost like a job title. So this, like for example, we can have an agent that is a research analyst. We can have another agent that is a writer, another agent that is a reviewer. So they can be very short titles, but they kind of provide like a general role of that agent within the team, which helps when breaking down work and assigning that to various agents. So the role is a part of that. And think of the role almost like when you interact with an LLM, right? You sometimes you assign a role to the LLM and say, you are a research analyst doing this, 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 and that helps kind of orient the LLM to its tone and audience and et cetera. It's sort of the same thing with the agent. The role helps orient the agent on what kind of tasks it will specialize in. So not only the role, but these three things work together to give background context about the agent and what kind of tasks this agent should be focusing on when we're executing an overall task. And so we already talked about the role. It specifies the agent's kind of specialty or expertise within the crew. We further can describe what its primary objective that directs its decision making. So this the goal of which is a string again, in when we define this inside of the agent object, this is going to be a string, and this helps again with delegation. So these couple of things work together to define, okay, what is this agent's primary goal? What is it good at? What does it typically do? This agent helps compare smartphones. This agent helps does research on XYZ. This agent's goal is to write up our itinerary and from our planning, etc. So we give the agent kind of a general direction. This is the kind of things you should be working on generally, is doing like this market research or whatever it is. So that's a string. Again, it doesn't have to be very long, but it's just a description and context for what this agent's primary objective is as part of the team, right? So we'll see an example of this because we're going to be defining multiple agents in our code. So we'll see some various examples of what good goal descriptions look like when we write them up in our code. Finally, we have a backstory which provides kind of a personality or context to the agent. And again, these three things, the role, the goal, and the backstory work together to orient this agent as part of its objective, its role. What is it good at? How does it conversate as part of the team? So, for instance, the backstory here is just a little bit of context. Like this agent is a former tech journalist with a passion for reviews. Um, and so this is kind of like in LLMs when you give a role to an LLM, like I said earlier, it's sort of the same thing. What is the background of this agent? And again, this is something that helps orient it to what is it good at? What types of tasks should it be taking on? A former tech journalist is probably going to be good at tasks like writing, doing background research, those kind of things. Okay, so these three things we will define. They're all strings. They're all string descriptions that we will set up in our code when we build an agent. The other two things are really, really critical here, which is defining our tools, which is just a list of tool objects. So we built two tools already. So we can basically, whenever we define an agent, we can reference those tools here as basically giving access for that agent to those tools. So again, these can be things that come from the Crew AI off the shelf, the toolkit. They could be custom tools like the ones we just built, but we'll be able to grant access to those tools to this agent by including them in this tools list for the agent that we build. So every agent, we should be specifying which tools they can use. Not only that, but we should be specifying which LLM they're going to use. Now, this is again, these two things, like the tools and the LLM, give us so much flexibility in identifying what this agent is capable of, right? Because depending on the tools it has access to and depending on the model that it's using to plan and think and conversate, that agent can be highly, highly specialized, right? Because this LLM could be like one of those special GPTs. It could be a fine-tuned model. So It could be like a really fine-tuned research model, like the consensus GPT that we looked at last week. Um, and so that may make it really, really specialized in that kind of task. And it has access to an LLM really geared towards that task, and that's been fine-tuned for that task. And every agent, we can change which LLM, uh, you know, which LLM it could use. Same thing with the tools, right? Every agent we define can have access to different tools. They don't all need to have the same tools. They don't all need to have the same LLM. So these make sense. Like every agent will have a tool list that we can define, and an LLM will be able to pass into the agent, and then it has sort of these roles, goals, and backstories to orient on what this agent should be utilized for. What kind of task should it be utilized for? What is its background? What is its role as part of the team? And that way we can delegate effectively within the team, and it can conversate, figure out who should tackle what, and when we do planning, who should do what. A lot of that is guided by the role, goal, and backstory. But not only that, but like what tools does this this agent have access to? It's also important because it kind of defines the capabilities of that agent. So again, these are all things that we have to set up in the code, and I'm going to show you that coming up shortly. Is the Slack channel still working? Yeah, it should be. Feel free to use it to ask questions or send me a question. It should still be working. Yeah, if you're still working on the projects, yeah, definitely ask any questions you have. Slack's still working. So just to show an example, before we jump into the code ourselves, here is an example of building a travel agent. You can see the main import here is from Crew AI. So we're using the Crew AI Python package. We're importing a generic agent. So that's our agent object. And you can see we're defining all those things we just talked about inside of this agent when we initialize it. So we're defining a role, we're defining the backstory, we're defining the goal, defining the tools, we're defining the LLM, and we're also turning on this, which is pretty standard to turn on, which is logging visibility, just to make sure every interaction with the LLM is logged. So we see the output of that, like what are we calling the model with, what are we getting in response from the LLM. And then you can see the tools. These are the tools we defined earlier. This would be an example of we're using this function, which is the search internet tool. We're using this function, which is the calculate tool. Those are the functions that we defined, which had the tool decorator. That's so in this tool list, it's going to recognize these as valid tools because they are inherited from the tool decorator, right? So they look like any other tool, and so they're valid to go in this list, right? This list of tools here that this agent has access to. Okay. So this is just an example, and we're going to build out some agents. And one of the things we're going to see is how do we instantiate an LLM that we can use as part of the agent. We're going to see that code as well in our agents file that we'll build. Okay, but you can see like building an agent is actually not hard. It's just defining the agent object and then all of these fields here that kind of outline the agent. And our goal in Crew AI is to build maybe a couple of these or a few of these that build out our team and then put them together in the crew, give them a task and then basically execute that crew against the tasks and then they can generate results by using their tools, the LLM. Um, that's going to be where this is all headed. Okay, so I wanted to go through building a few agents for our demo. So we have those tools in hand as part of the project we were talking about earlier. And we're going to build a few agents here to make use of those tools and to um, collaboratively help with a trip planning workflow. So we are going to build a few agents. We're going to have a city selection expert, which is for determining where we should go in terms of travel, and then a tour guide agent to come up with an itinerary for that destination, and then an expert travel agent to help us with budgeting and those kind of things. So we will uh, um, build out those three agents in our code, which will all follow the same kind of object setup that we just saw. So we're going to build three agents that are all going to basically follow this kind of setup of defining the agent and then just changing out these different parameters like a role, backstory, goal, tools, LLM. Okay, so let me go over to this and let me share the demo file with you. So this would be this one. Okay, so I just uploaded the demo file that we're going to look at, which is going to be for creating the agents. Let me share my screen. Okay, so as I said, we are going to write some code that's going to build these three agents, and it's mainly going to follow that setup we just saw with the object, right? So um, defining the role, the goal, backstory, the tools, the LLM. Those are, and what we're going to do is put all of those into an agents.py file. And again, this is if you're running locally. If you're in Colab, you can just put them in different cells. You can build each agent in a different cell, essentially. But we are, if you're running locally and want to organize this, you're going to put this code inside of an agents.py, which I'll share with you because I already have it built out. Three agents that we're going to build. And essentially, what we're going to do is build all of those agents as part of an overall. We're just going to organize it so that these, like, this is a choice. You don't need to do this. We're going to organize it so that these three agents are part of this class, just to organize it. So all of those agents are part of a generic travel agents class. It's not necessary to do, but it helps organize our code so that all of these agents are accessible from this one class. So again, we're going to create an agent.py. We're going to have these dependencies, which I'm going to, again, share the code with you so that you have it. Notice a couple of those dependencies are our custom tools. So we have a couple custom tools there that we already built, like our search tool object and then our calculator tool object. So we're going to utilize those in our agents. Um, we have our Crew AI agent we're importing here, just like we saw in the example. Um, One thing that's new is this. So this is basically giving us an option for what LLM we want to use, which is in particular an OpenAI LLM. That's a choice. You can use different LLMs, like you could use Gemini, you could use something from Hugging Face. Um, there are many different integrations for LLMs that we could use. This demo in particular assumes that we're using OpenAI LLMs, but we could use whatever one we wanted to. And so that's completely interchangeable, but this will be an example of using OpenAI in particular as we build out our agent. Of course, it's going to need LLM access, in this case, an OpenAI LLM. So again, I'll share this code in a moment. You can see that we're building a travel agents class, and it's going to contain all of our agents are within this class, and that's purely for organization purposes. There's no necessity to do that, but it's just to organize our code so that those are a part of this one class so we can reference that later. But is it strictly needed? No, not really. Just for organization. Uh, so they used to be, that's a great question. Are these GPT models accessible? They used to be, but I don't think they'll work now because I think these API keys are expired. Um, but uh, I'll show you where you can swap that out to a different model, like Google or Hugging Face, and so you can utilize like a free API to call, or if you have your own like OpenAI API key, you could swap that in here and use that. Um, but unfortunately, no, you would need the OpenAI key to do it. No worries, no worries. Okay. Can you use local LLM? Yeah, you can. It's possible. Yeah, you can use that. Okay, so let me come back to the LLM part and we'll see how we can swap that out for different LLMs. But what I want to get to is the agent part. So as part of the class, we are defining three agents. One is going to be an expert travel agent, which looks like this. So notice that we are defining an agent here, which is the Crew AI agent. And what we're doing is setting up these various parameters, right? So we have our role, which is expert travel agent. We have our backstory, which gets a little cut off here, but it's just some background information, right? I'm a seasoned expert in travel planning and logistics, decades of experience, blah 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 blah, right? And you'll see the full string in the code when we go to it. We have its goal, which is plan a 7-day trip with day by day details, including a budget, packing tips, and etc. You can see which tools it has access to. So we're only giving it access to these two tools. But again, like we could give it access to a broader range of tools if we wanted to. But that's our opportunity to put in the tool list what tools we actually want to have. In this case, we just have an internet search and calculate. We're turning verbose on so that we get good logging. You generally want to have that on unless you don't care about seeing all those interactions, but generally you do, especially when you're debugging. And then we're setting our LLM to be one of those LLMs that we defined earlier in the class. So in this case, the OpenAI GPT. But of course, that just could reference any of those models we put in earlier. Um, as part of the setup. So again, I'll point that back out in the code when we get to it. Yeah, Gemini could be an alternate. The reason I brought up Gemini is because you can get a free API key for Google by going to Google AI Studio. If you search the Google AI Studio, you can create a free API key there and use it with one of the Gemini models for this LLM. You can also use Hugging Face if you generate a token on Hugging Face. You can use one of the free models there too. You can even download it locally and use it locally. Yeah, Anthropic. Yeah, you can use if as long as you have an API key. Um, Yes. So basically so let me go back to there are variations on this LLM that come from different LangChain providers. So see how we have LangChain OpenAI. Um, You can use LangChain, Google Gen AI or LangChain Anthropic. There's various models you can grab from the different integrations with different models there. You can do probably the best option is for free is probably Hugging Face. Probably the best option is to use like a Hugging Face model here, um, which would involve swapping out this. So in the code, that would involve swapping out this chat OpenAI for like a Hugging Face hub model, and then like downloading the model locally to be in memory. Um, Probably be the best option because you could use it for free. Um, so. I'll show you where to do that once I open up the code. I'll show you where to do that. But yeah, it's basically here we could swap it out for something from Hugging Face. I think that'd be either the two best for free would probably be that and the Google Gemini, because you can get a free API key from them and use Google models. It depends on the model. Like I think a very cheap, like an older I say cheap, but like very lightweight model, I think would be fine. So like one of the older QNs might work. Um, that's probably fine. Might take some like playing around with to get correct, but yeah, I think it'd be fine. I don't think it would require anything like to use one of the larger, like newer ones, probably. It would require a better hardware, but you might be fine using an older one. If you use something like Google, that's just calling the API, so it's not really going to cost you. You don't need hardware to do that, right? Because you're just calling the API. But there is a limit. It is free, but you'll hit a limit eventually if you're using it a lot. But you can get an API key for free and kind of use it um, through again, if you go to Google AI Studio, you can get a free API key from Google to use. By the way, this is the travel agent. So in a similar way to this, so we just saw the travel agent. In a similar way to that, we can build the city selection expert, which is looking at building travel destinations. Now, something interesting about this is because it's not doing any budgeting or anything, it's just selecting a place to go. The only tool it has access to is the internet search. It actually doesn't need the calculator object because it's not going to be doing any kind of budget calculations or anything. So it only gets that tool, right? So that's a way for us to limit what tools it actually has access to. And this one doesn't need access to anything beyond just the internet search for picking the travel destination. So we have an agent with this city selection expert with a pro at finding destinations, and its goal is finding top cities to visit, considering weather, seasons, budget, which would be information we would have from, you know, uh, we would already have from the prompt, usually from the information. Then create, now we have a local tour guide. So this would be very similar to the other setups we've had. So we're going to see, and again, I'm going to share this code with you in a moment, but we're going to have an agent that has this role, backstory, goal, again, just the internet search tool, doesn't need anything else, and then an LLM. You can see like just going back to this call out of when we define this agent, that's our opportunity to, again, specify what specialty tools or LLMs we want these agents to have. In this scenario, we're basically giving it the same LLM to use. We're not really specializing it to use a special LLM, but we would have the opportunity to do that if we wanted to, right? We could change that LLM there in that argument Same thing with the tools. Every agent can have different tool access. In this situation, this one only has internet search, but it could have lots of different tools if we needed it to. All right. So let me share the code file with you that has all of this. So this would be again in our agents.py. I'll share that with you and then kind of pop over to the VS Code to show you that. So here is our agents.py. Now, if you're running in Colab, you're going to need to pip install CrewAI and LangChain OpenAI. So you'd want to run those two in order to get access to these two things. So to have the LLM access and to have the CrewAI access, you would want to run that pip install in your notebook. Or locally, you would do the UV add. If you're using UV or even pip, you would do UV add CrewAI and LangChain open AI. So you want to run that command, which would add those packages to your virtual environment. Again, that's if you are using UV locally. For me, it's going to see that I already have those. And what you should see is those should pop up here in your dependencies list. So we have those two guys added for this agents file. Okay, so we have those two things. We want to have those installed. And then if you're in Colab, you basically just want to copy all that code and put it in a cell and run it. That would be fine. Just copy all this code and put it in a cell, which is just basically the class to contain all of our agents. So this is going to contain all of our agents that we're building. Um, you can see the backstory is a bit of a string here. I'm a seasoned expert in travel planning and logistics with decades experience. I'm here to help plan your perfect trip. Then plan a 7-day trip with day-by-day details, including a budget, packing tips, and safety recommendations. And it has two tools. It has the search internet tool we just built and the calculator tools that we just built. Um, and it has access to this LLM. So again, if you wanted to change the model, this is where we could do it. Basically, we could set up a new model. Um, you know, it, Depending on what we use, we may have to pip install different extensions. So if we wanted to use like Hugging Face, we may need to install, especially locally, like different LangChain Hugging Face tools to get it to work with that. But essentially, what we could do is have a new model like Gemini. Um, and we just need to we could pass in our model version here, like 2.5 Flash or something. And then what we need is to pass in the API key, which we would need to set inside of here somehow. So you would have to put in your API key here, whatever that is. um, we could set that. So if you're using Google, you can use an example like this. Um, and you could just set, we don't even need temperature. Don't really want to change that. But this is the minimum, is just specifying which model we're using and then specifying an API key. Again, you can create an API key by going to, let me make a comment here. You can go to Google um, dot AI, or I should say AI studio dot google.com to create a free Gemini API key. So that's just an example. You can go there to create a free key, and then you just would put that key here, and then you can use the Google models.
And that brings us to the end of this Microsoft AI Engineer Capstone session. In this video, we explored 3 capstone projects: autonomous driving, tourism, recommendation, and sales forecasting. We also reviewed the important machine learning, deep learning, computer vision, recommendation systems, and data analysis concepts needed to complete these projects successfully. We also looked at agentic AI and understood how frameworks like LangGraph, AutoGen, and QAI can help us build AI systems where agents can plan, use tools, collaborate, and complete the task. The key takeaway is simple. This capstone is your chance to bring everything together, from data analysis and model building to computer vision, forecasting, recommendations, and AI agents. This session will help you move from learning AI concepts to building real-world AI solutions. If you found this video helpful, make sure to like, share, and subscribe to Simplilearn for more videos on artificial intelligence, machine learning, deep learning, generative AI, and the latest tech skills. Thank you for watching and see you in the next session.